you're just hoping to get some initial data to, do more longer simulations, you don't need to spend much time on generating different, basically different conformations, because the conformations that you will get in 100 nanoseconds will be pretty highly correlated. Yeah.
But in general, we are now releasing, I think in a couple of months, a workflow where we combine MD and docking for antigen and antibody.
Yeah.
Between GROMACS and ADOC. If people are interested, they can just follow what is going on the Twitter account of LinkedIn from BioXcel, and then we will get information there. They are also, I think, seminar. They are also around some talks. Yeah.
Yeah, and it's important to stress here that which tool you pick matters a lot. So Haddock allows some flexibility in the binding site, whereas something like AutoDoc doesn't. So that that makes a difference as well.
Anyway, the tools that I was mentioned was GMX cluster. I'm sorry, my kernel decided that I cannot run anymore on the Jupyter notebook, so I can restart. But I think now we are almost at the end of the section, so that is not worth. Yeah. There are any other questions coming up?
I think that was it.
Okay. So shall we take a lunch break now? It was the plan. It's correct. Oh no, sorry. We have just a break.
No.
A break.
Oh,
sorry.
break.
Yeah. It's a 20 minutes. 20 minutes break.
Yeah.
Yeah. Okay. Great. Yeah.
All right. So back at 1.
Yeah. And then we will have Joe Jordan with Chromax feature. Yeah.
Cool.
Okay.
Institute of Technology, Sweden, and I am the project manager for something called Mblib, which is one of the features that I'll tell you about in this talk. So there's going to be 4 parts. There's going to be a short introduction. Then I'm going to talk a little bit about APIs, or application programming interfaces. And then I'm going to talk about some of the performance features that are sort of the hallmark of GROMACS over the years. I'm going to talk about some other features, some nice, scientific features that we've added that are interesting. So, all right. So I'll actually start with some acknowledgements. So if there's anything that I'm talking about here, all of these slides are just taken from other BioXcel or from BioXcel webinars. And so you can actually just go to the BioXcel website and try to find that webinar and, learn in more detail about any of the topics that I'll discuss. So I should acknowledge the people who made the slides. So Mark Abraham, Paul Bauer, Christian Blau, Bear Kess, Eric Gergang. Some of the slides are from a talk that Sebastian Keller and I gave, and Karsten Kutzner. And additionally, I should, acknowledge basically all the GROMACS developers over the years, of whom there are many. So when you don't give the -quiet option and you run GMX whatever, you get a full list of everyone who has ever contributed to GROMACS. It's very big and growing all the time. All right, so what do you do with GROMACS? Hopefully, if you're in this workshop, you already have some idea about the answer to this question. Of course, you could do biomolecular simulations. You can also simulate polymers. You can simulate lots of interesting stuff. So one thing I'll say, before going much further, and as part of the introduction, is that we put a lot of effort into the documentation being as comprehensive as possible. So we have a lot of documentation. If you have an answer, or if you have a question and you spend some time in the docs and you don't find an answer, another thing you can do is you can go to the user forum and see if someone has already asked that question. And if they haven't, then you can ask yourself, and generally, you can get an answer in some amount of time But definitely it's important to start with the docs. You know, they're not just useful for understanding how to use GROMACS, but I would say are an extremely useful textbook for statistical mechanics and understanding the actual physics of ND simulations and, you know, what you're simulating. So it's very useful for that regard as well. All right, so GROMACS has an annual release cycle. So we try to release, you know, and for the past several years, we have released a new version every year. And so in addition to having a major release once a year, we also have several point releases throughout the year. And so the reason we do this is because, you know, everyone's human, everyone makes mistakes, and sometimes users report bugs, and we want to do our best to fix those issues, you know, relatively as they arise. So you may be thinking to yourself, oh my God, GROMACS has bugs, you know, I can't trust it. So a couple of points I can make here are that the bugs tend to be in real edge cases, things that we're not, you know, seeing much use of. So if you're doing kind of a normal run-of-the-mill simulation, it's extremely unlikely that you're going to get any bugs. Another thing that sometimes you can see people saying is like, oh, well, you know, GROMACS has these bug reports and has release notes saying which bugs have been fixed and the other MD codes are not. And that's not because the other MD codes are not necessarily having any bugs, it's just because they don't have a public way to document them. So one thing that I think is actually really nice about GROMACS is whenever you download a new release, you can go look at you know, which bugs have been fixed and see if any of the simulations you have been running might have been affected by one of them. So that's a really useful feature, we believe. So talking a little bit about Chromax Impact over time. I mean, of course, we're all here because we know GROMACS is useful, but you know, we're not the only ones. So this slide is already a little old, but it's showing you know, a huge number of of citations of the various GROMACS publications over time, because you know, it's software that a lot of people, you know, are using to do really interesting science. All right, so now I'll talk a little bit about APIs, which again, API stands for Application Programming Interface. So historically, if you have wanted to do an MD simulation with GROMACS, you know, what you've had to do, you know, what we talked about a little bit in the tutorial with Alessandra is, you know, have some kind of bash script or some Python script, you know, some way to manage your workflow. And so we're trying to develop APIs to make it easier to do this, so that you can more directly interact with the code and, you know, get to having the data you want in a quicker amount of time. And so I'll talk about 3 different APIs today. So one of them is the GMX API. So this is a very high-level API that you can use for basically setting up and running the simulations. So this can be a replacement for instance, bash scripts that, you know, maybe have been handed down from previous grad students in the lab and developed over time. So another API I'll talk about is Mblib, which is a project I've been working on for the past few years. So that's a lower level API where we're exposing the various performance aspects of GROMACS. And then I'll also say a few words about something called the Modular Integrator. So what is the GMX API? So it's been developed by Eric Ergang, who is in the Peter Kassem lab. So the idea is basically, well, there's a strong need for APIs to access MD tools. So this is a slide from 2018, but showing that already then there had been a number of BioExcel webinars about various APIs to access MD tools and what the needs are. So this, you know, at that time already was strongly pointing to this being something that a lot of users wanted. So how do you use the GMX API? Well, it's fairly straightforward. So you know, this is all in Python, and so basically you read in some files, and then you can, if you want, add some restraints. basically add whatever kind of forces you're interested in to your system, and then you can run your system. So in a little more detail, so what is the Python command doing? So basically, Gmx API is not just a wrapper around the Gmx binaries. It is actually basically a workflow management engine. So you give it some input data like your Tpr files, and specify other things like how many processors, any of the options you could imagine giving to Gmx MD run, for instance. And so this all gets passed on to the MD engine. So another cool thing is you can add forces to your system in a nice way without too much extra work. And so Gmx API will try to build a work graph, and then it'll basically execute that work graph. So it'll send the data off to the MD engine, and you can do ensemble calculations and other kinds of things. So here's a few examples. So in the first code block, you can see creating a workflow from one Tpr file, and then running a simulation. So that's very straightforward. But you can also pass an array of inputs. So you can pass in a number of Tpr files and run. And of course, there are many options that you can set to from Tpr. So you can set the number of thread and PI, ranks. As I mentioned, basically any of the flags that you can imagine passing to Gmx MD run, you can also pass to the workflow manager and have sort of one place that is actually setting up and running your simulation. So that's very nice. So I also mentioned restraint plugins. So how does that work? So for instance, let's say you have some system and you have some experimental data that tells you, for instance, the distance between the two particles or two parts of your system, and you basically want to constrain your system, to lie in this range with a harmonic spring, for instance. So you put in you make a list of params. Hopefully you can all see my mouse okay. So for instance here, you would have atom 1 and atom 4 would be where the harmonic bond is going to be applied. And then you have an equilibrium distance and a force constant. And so then you can just add this to the workflow engine. And now when you run your simulation, it's constrained to these distances. And so, yeah, so this is a very powerful way to add forces. Of course, you could do more complicated things, and you can go read the manual or go watch the webinars to try to learn more about the types of workflows that you could do. But hopefully this is at least a brief overview of the utility of Gmx API, and we hope in GROMACS to have more development efforts so we can actually make Gmx API nicer and nicer over time. But it already is shipped with GROMACS, so you can already start using it today, and many people, I think, are already starting to do so. All right, so another API, which is, again, what I've been working on is something called Mblib. So this is a non-bonded force calculation library. So the non-bonded forces are actually the most computationally intensive part of a molecular dynamic simulation. So depending on what your input, what your system is, it can be, up to 60 or 80% of the total compute time. If you actually go and, look at the compute usage of various supercomputing centers, just this calculation can actually be up to 20% of, the total usage of some supercomputers, if they have a large fraction of GROMACS users. So, it's, and GROMACS has over the years put a lot of effort into having a very high performance non-bonded force calculation engine, because this is necessary to have high performance molecular simulations. All right, so And so just to round out, you want to have a nice interface that makes it easy to call this calculation without having to know too much about what's happening under the hood in GROMACS, basically, but still exposing the performance so that you can add forces or experiment with new simulation methodologies in a relatively quick time frame. So we have a topology specification, which at some point in the future, who knows, may end up being becoming the GROMACS topology specification, with a bit more work that I'll talk about later. So a system has particles. A particle has a name and a mass. It's pretty straightforward. So here we're trying to build some water molecules. So you can add interactions. So these are Lennard-Jones parameters to your oxygen and your hydrogen and your water. You can add exclusions. So exclusions are basically saying if you have two atoms that are directly bonded, there's not much point in calculating the non-bonded interaction because the bonded interaction will overwhelm. So you can think of this as a performance optimization. And you can add bonds, of course. So a bond in this case is just something with an equilibrium distance and a force constant. And so, that's your whole specification for water. Of course, you can't really use this for an MD simulation because all the water models used in actual MD simulations have constraints because water ends up being a large part of the system. But you can imagine, that using this, it's illustrative of how you can set up an Mblib topology. And so to summarize, basically you have particles and bonds, and these go into molecules, and these create a topology. And so if you add these to, if you set some options and you give some coordinates, you can send all of this to the Mblib non-bonded API and get back some forces. And so this is really nice because the topology specification, is actually just generating some input data of elementary types. So, that code looks something like this. So, you have some particle types, some non-bonded parameters, charges, and so on. So you generate your force calculator, you update a pair list, and then you can call compute straight away. And so you actually don't have to use the Mblib topology specification. You can actually use a TPR to get the data you're interested in. And so then instead of using the topology, you would use the data from the TPR reader. The code looks pretty much the same. And so the really nice outcome basically of this is that you can write an entire MD mini app, on one slide. And if you ever take some time to go look at the GROMACS code base, the code in a file called simutil is a few thousand lines long. It has much more performance than this mini app, but this is something you can look at and intuitively understand. So you set up your non-bounded force calculator, your listed force calculator, and your integrator. And it's just a simple leapfrog integrator. And in one step, in one slide, you have a full, MD simulation engine. So this is extremely useful if, for instance, you want to play around with writing new integrators, or, it's very easy to add new listed forces, new types of bonds and angles and such. So here's an example of a workflow. You could imagine you want to do some kind of replica exchange. And so all you would need to do is generate your two force calculators and have your two integrators and have some kind of integration loop like the one I showed you a moment ago. And then periodically swap the velocities, presto, now you've got a replica exchange implemented in a few lines, which is very exciting, we think, and can help certain scientific use cases, and can also help GROMACS developers going forward. So the last API I want to talk about is the Modular Integrator. So it's a modular integration approach. So this actually ends up looking very similar, I would say, to the GMX API. So the Modular Integrator is essentially a task graph generation engine, a workflow engine. So when you're trying to update the positions in your MD simulation, there are a number of steps. You might need to do constraints, restraints, updating the coordinates might need to happen more than once. And so it's really useful to be able to chain these things together in an arbitrary order, which, historically has not been possible in GROMACS, at least, because the code is developed over a long time. And so the idea of the modular simulator is to basically wrap all that code so that you can quickly tinker with your integrator. And this is extremely useful for things like free energy calculations, where, in order to have the correct statistical properties of your system, you might need to have a very specific order of things that happen during the integration. And so this is also why in Mblib, there's a listed forces and a non-bounded forces API, but not really any update or integrator API. And the reason for that is because this work is ongoing. So this work has been done mostly by Pascal Meritz and the group of Michael Schertz. Okay, so are there any questions about the APIs before I move on to talk a little bit about performance? Okay, well, I will move on, and perhaps if people have questions, they can also get answered at the end.
Sorry.
Oh, yes. Yes.
I think you have. Sorry, Alexander. I think that Joe has a question on chat, and on one.
On the Google Doc. On Google Doc, we have answered it. On Google Doc, we have answered it. Was the question I tell you, because maybe you address later in your presentation. I will also tell that one to you. Wait, that I found Google Docs. How can you optimize GROMACS performance for CPU only in HPC cluster? So we have answered with the link, because I think it's easy, with the link to the manual page, but maybe further in your talk, and also maybe something will be said by Mark tomorrow, that is more on GPU performance.
Yeah, so I'll talk a little bit about performance. I won't really say much about how to get optimal performance, but
okay. And the other question, but I didn't answer since I didn't understood the context, was on the chat, is can you test multiple parameters in the MDP file to test different parameters and see their effect on output without output automatically named accordingly?
Yeah, so I'm not sure I understand the question either, but I mean, in general, it's very hard to test the impact of some MDP parameters because they might have very subtle effects on the statistics of your simulation, whereas other MDP parameters, if you change them, your simulation will immediately break.
Yeah, so, but to avoid confusion, I want to make a point. One cannot specify the several MDP parameters in the MDP file. So you have to have only one option. It's not, for example, that if you have integrator, you can put steep descendants, MD, and so on. That is not allowed. You have to have one value. I don't know. I asked the person maybe if you can clarify in the Google Doc.
Can you hear me?
Yeah, sorry. Yes. Could you amplify it in the Google Docs?
Okay, I will clarify in the Google Doc. Meanwhile, we can't specify many parameters in the MDP file. So I was talking about the workflow management presented at the beginning of the talk. So is that one, can we use that one to say, okay, for example,
So I understand your question. And so one feature that is lacking in the workflow management is the ability to actually edit Tpr files. So you can, of course, basically write a loop and call GROMPP, either at the command line or in the GMX API. It's easy enough to write a loop and basically have different MDP files with different parameters and call GROMPP, with all of them, and then run them. So that you can certainly do, but it is not possible to generate one TPR file and then edit that on the fly and send that to different simulations. So I hope that answers the question.
Okay, I got it. Thank you.
Great. All right. So then I think I will move on and talk a little bit about performance. All right. So performance, I would say, is one of the hallmarks of GROMACS. This is something that the GROMACS developers put a lot of work into, to get maximum performance. And this is very important because better performance leads to faster answers to our scientific questions. So I'll go into a little bit of the history of the performance improvements that have been made over time. So long ago in GROMACS 4.5, which is what was available when I started my PhD, there was no GPU acceleration. So everything ran on the CPU. So schematically here, we're saying that a step consists of pair search, short range non-bonded, PME, which you can think of as long range non-bonded, bonds, and included in bonds, we also have angles, dihedrals, etc., and also update, which is changing the positions. And so in GROMACS 4.6, a port of the short range non-bonded forces to the GPU was enacted. And so this was enabled by having a buffered pair list. And so what does that mean? So basically, if you want to simulate a bunch of particles, obviously you have to compute the forces between the particles. If you have a number of processors or even a number of GPUs, you need to split up the data so that all the slots in your GPU or all the processors can be used. And so the non-bonded force calculation gets some speed up by basically having what we call halo particles. So particles that are a little outside the separated domain that you've decided. And so that way you don't have to do as much communication between your different threads or different nodes or whatever. So in 2018, something called dynamic pruning was added. And so this is a performance improvement because it basically means that you need to recompute the pair list less often. So I won't go into the details, but this is a useful thing. And so then eventually also the particle mesh Ewald was ported to the GPU. And so already at this point, with PME offloaded to the GPUs, this moves the optimal hardware balance towards using GPUs because you don't have as much weight basically on the CPUs anymore. So here's some further updates. So in GROMACS 2019, the bonded or listed forces were moved to where now they can also be run on the GPU. And then in GROMACS 2020, the update and constrain modules can now run on the GPU. So what this means is you can actually basically run a full ND step for certain input configurations on the GPU, and then you only actually need to use the CPU if you want to recompute the neighbor lists, or if you want to write data to disk. And so especially if you have a very powerful GPU and not as much CPU, this can be great in terms of performance. So here's a slide that a little bit gets at the question that was asked about optimal performance. So this doesn't say anything about how to get it. And this slide is also a little bit old. It's from 2018. So I would say don't spend too much time looking at the actual numbers. It's just kind of the shape of the graph. So on each of these graphs, you have the number of CPU cores per GPU on the x-axis and nanoseconds per day on the y-axis. And it's for two different systems, basically. And so all this is showing is that you get speed up with as you increase the scaling up to a certain size, and then after that, the speed up is sort of flat, and so you're not really getting any improvement at that point. And so the reason that I show this slide is really just to say that if you are concerned about getting the optimal performance, you need to do some benchmarking and figure out, how many CPU cores, how many GPU cores. Unfortunately, there's a lot of options. So one thing we really want is to have some kind of automated tuning that determines which things should be run on the CPU, which things should be run on the GPU, how many threads, cores, GPUs, can be allocated. So one additional thing I'll say here is that it's a common mistake to just say, I've got my simulation system, maybe it's 100,000 atoms. It's a typical simulation system size, I would say. And, I've got these nodes that I have access to, and they have, 16 or 32 cores and 4 GPUs, and I'll just put my system on the node and I'll ask to use everything because, of course I want to use everything I can. And you actually might not get very good performance doing this because, your system is basically not big enough. So we have some warnings that can be triggered. Basically, if your system is not big enough to utilize resources, but you have to pay attention to them. And so in such a case where you have one of these fat nodes with a lot of GPUs, it can actually be more useful to run 4 or 8 separate copies of the simulation you're interested in simultaneously than one using all of the hardware. And so this is something that is feasible using the GMX API. And of course, you can also do it on your own using Bash and Python scripts. But it's something that we would like to make a little bit easier because this is, this is something that gets at the ultimate question of, getting answers to scientific questions faster. So a related point that I can make is about basically the total cost, in terms of hardware and energy for generating a trajectory. So again, this slide is a little bit old, but it illustrates a couple of useful points. So one is that newer versions tend to have better performance. So, don't use GROMACS 4.6, don't use GROMACS 2018, use GROMACS 2021. And, in next year, use GROMACS 2022 and so on. So that's one point. Another thing is that you can clearly see is GPUs are generally a major win in terms of a cost-benefit analysis. The cost per microsecond in euros is much higher on this chart for the no GPU systems. And that of course depends on the type of GPU you get. If you have a top of the line GPU card, it can be very expensive. Although generally you don't need to have the very, very best. And GPUs, you can, get away with something a little smaller that, still gives you a lot of bang for your buck, so to speak. And then the other point is that in general, newer hardware will give you, better results in terms of energy efficiency, specifically because as new processors come out, they have smaller die sizes and therefore use less energy. So, there's a lot of information packed onto this graph. So that's why I show it. So it's an important consideration to think about, over the whole life cycle of a cluster, what is, how am I going to be able to do the most simulations, basically. All right, and so some other types of performance work that are ongoing in GROMACS. So SYCL is basically a programming model that is being developed for hardware accelerators, GPUs. So I would say the development there is being spearheaded by Intel, who is coming out with GPUs in the hopes of competing with NVIDIA. And so now also AMD is coming out with GPUs that will use something called HipSYCL, which is basically a SYCL flavor. And so, for instance, the Lumi machine, which will come online for European supercomputer users, at some point in the not too distant future, will have these AMD GPUs. And so we're working hard to do our best to make sure that when GROMACS 2022 comes out in January of next year, hopefully it'll come out in January, it'll just work to run on Lumi when that system becomes available. Yeah, so in addition to trying to support SYCL, we've also had a productive collaboration with Riken, the major Japanese supercomputing center, who last year, I guess it was, or maybe earlier this year, their Fugaku machine debuted at the top of the top 500 most powerful supercomputers. So this machine, Fugaku, uses ARM, SVE, and so via collaboration with them, we support that machine, and any other machine that has ARM SVE and compatible compilers and tool chains, it should just work. So you should be able to run on this hardware, and this is one of our major goals, is that whenever new hardware comes along, and they seem to come along a lot these days, that we try to support it, because it's important to have some competition in terms of what hardware you can buy. For a long time, it's sort of been NVIDIA or nothing, and so this has changed rapidly in the past few years. This is very exciting, leading to a lot of development in the HPC landscape. Yeah, so one other feature that's related to performance, which has already became available in GROMACS 2019, is something called update groups. So I mentioned already that if you want to split a simulation, basically you have to pick some partitioning and say which particles are going to be computed on which nodes. And so at some point in the past, we basically said, it's easy from a geometrical perspective to just divide everything into rectangles and send particles for computations to whatever rectangle they end up in. And at some point, we realized, we were spending basically losing a lot of performance, because we were having to communicate a bunch of atoms that were not, that could easily be in another domain if we, drew curvy lines instead of straight lines, basically, such that you could have all of the particles in one molecule in the same domain. So this really reduces communication, which is a major bottleneck in HPC systems. All right, so I'll pause for a second to see if there are any questions about performance now that I've talked about that a little bit. Nothing? Okay.
Nothing.
All right, I will go on then. Okay, so now I'll talk a little bit about features. So the features I want to talk about are AWH, the accelerated weight histogram method, which I'll just briefly mention before, Berkes will explain it later today. I want to talk a little bit about density fitting and also about multiple time stepping. All right, so one thing that is a relatively new feature in GROMACS is using accelerated weight histograms to do alchemical free energy calculations. And so what do we mean by an alchemical free energy calculation? So that's basically, it's like alchemy from the Middle Ages and early modern period, trying to turn one substance into another. So, you can't do it using mercury, but you can do it using a computer. You can just change the parameters of your system on the fly if you know what you're doing. And so this can be useful, for instance, for calculating solvation-free energies, where you have a solvent that you want to, or a solute that you want to move into a solvent. Or for instance, if you're interested in delta G, so let's say you have an enzyme and you have two inhibitors, I and I prime, and you want to understand their relative binding free energies. Well, one thing you can do to try to get an absolute binding free energy is basically to use pulling to move the molecule from solution into what you suspect the binding pocket to be. You could also run a long simulation and hope for it to bind. Unless you have a huge amount of processing power, this is not a very good choice, because you also won't get very many binding events, so you won't have very good statistics there. And so if you're really interested in getting relative binding free energies, One trick you can do is use thermodynamic cycles to exploit the equivalence between delta G1 minus delta G2 in this diagram in the lower right versus delta G3 versus delta G4. So basically, like I said, it's hard to actually move the inhibitor into the binding pocket, but it's really easy to do one simulation where you change inhibitor I to inhibitor I prime, both in solution and in the binding pocket through a non-physical pathway. And using this, you can actually get the relative free energy differences between your two inhibitors. So one problem is that, of course, if you have different parameters, maybe even different masses and charges, you will not have phase space overlap. So you could imagine this 2D projection of phase space being, for instance, charges and masses, or charges and Lennard-Jones parameters, something of this nature. And they don't overlap because they're completely different, right? So you need to define some kind of path. Again, it doesn't have to be a physical path. It can be whatever you want that connects these two systems. So you have to do that. But once you've done that, then you can use AWH to dynamically explore along this path and basically give you the free energy of this alchemical transformation. Yeah, and so the ultimate goal is to generate a free energy landscape, that looks something like this. Free energy of binding, for instance. You could imagine it as, and the way you do it is by biasing your system so that you can freely explore along your reaction coordinate here. Yeah, and so Bearcats should say more about this later, but I just wanted to mention specifically the alchemical free energy because, it's already been a feature in AWH using the pull coordinate, the pull code in GROMACS for a while, but this is a somewhat newer feature, so it's useful to highlight, I think. So another cool feature that's been in GROMACS since 2020 is using density-guided simulations. So this is basically automated fitting to cryo-EM densities so that your structure can match an experimental structure. And you can also use it to see structural transitions between states. So how does it work? All right, so you have your structure, which you got from somewhere. It could be homology modeling, whatever. It could be a previous crystal structure, and then you have your reference density. And so then you do some simulations of your structure, and you find, darn, it doesn't spontaneously. The density of the simulated system doesn't spontaneously drift towards overlapping with the reference density. So what do you need to do? Well, you define a similarity gradient, basically a place where there's an overlap between the densities, and you just try to go down that gradient. So conceptually, it's very straightforward. Mathematically, it's also not so complicated. From a code perspective, it's a little bit of work, but you don't have to do any of that. You just have to basically set some MDP options. So the minimal thing you need to do is to have something called reference.mrc in your MD run directory, and then turn density guided simulation active to yes. So I should say also that it doesn't have to be an MRC file. You can use any of the standard cryo-EM density format files, as long as the data is on a regular three-dimensional grid. So in addition to this most simple way to set it up, there are many more advanced options, which you can learn about if you go and watch Christian Blau's BioExcel webinar on the topic. So I'll say, this is also an area where we are interested and hopeful to have some future developments. If you have, basically, if you do some fancy statistics, you should actually be able to take the minimum free energy path to the to get good overlap, of your simulation and the reference density. And this should actually tell you something about the differences in the probability distribution between force fields and different experimental conditions, which theoretically should give us useful insights into biomolecules, and could be used in the future, you could imagine to parameterize force fields. And again, this is not something that from a scientific question we're working on, but it's something that we're thinking about, basically exposing features of if it's something that's going to be interesting to users, perhaps. So another feature that has come in GROMACS 2021 is something called multiple time stepping. And so one of the major limiting factors of doing an MD simulation is, as Alessandra mentioned in her intro to MD talk, is that you have to use a fairly small time step because the vibrations of hydrogen atoms are fairly fast relative to the rest of basically the rest of the system. And so one thing that GROMACS has used in the past to get around this is something called virtual sites, which you can think of as a constraint on the motions of the hydrogen. And so with this, you can increase from 2 femtosecond time steps to maybe 4 or 5 femtosecond time steps, and get a nice speed up. But it would be nice actually to instead of constraining the hydrogens, actually just compute the hydrogen interactions, or and update the hydrogens based on the forces you compute at a frequency that is relevant to the motions of the hydrogen, and only do that for the hydrogens, and then at other time steps, which we're calling fast time steps, then you would compute all of the interactions, the non-bonded, the PME, and so forth. So this is available in GROMACS. This has a number of nice features. So the integrators are symplectic. So what that means is that energy is conserved. And so, you can improve performance. Theoretically, you can improve performance by calculating the forces less frequently. So it's not so hard to get this working. There's some MVP options. So you set MTS to yes, and then you pick which things are going to happen at level 2 versus level 1, basically on the inner and outer steps. So this leads to a small to a moderate performance gain, and actually a large performance gain for very high parallelization. So if you have a very large system, this can be very effective. So the original idea was that you'd be able to replace having a time step of 4 allowed by virtual sites with using the multiple time stepping. Unfortunately, we discovered a little bit of instability, and so we're actually doing some research to try to figure out what the limitations are, if it's related to force fields or if it's related to something else. But hopefully in the not too distant future, we will be available, or it will be possible in GROMACS to use multiple time stepping very, very effectively to increase the efficiencies of your simulations. So this is an active area of research, especially by Bearcats. So one other feature that I'll mention, so we talked a little bit in the hands-on tutorial about equilibration. And so traditionally, it has been the case that you run an equilibration step where you use a Berenson thermostat, which decays exponentially to the target value, but which does not conserve energy. And then in production, to switch to a second order barostat, such as a Nose-Hoover, for instance. So with stochastic cell rescaling, you basically get both features in one integrator. So this is nice because this means, for some systems, you can actually just combine your equilibration and production run and just throw away, the initial period of your simulation. It just works. So this was part of a collaboration with Giovanni Bussi that went very smoothly. So that's a feature that's in GROMACS 2021 as well. All right, so some long-term plans for GROMACS. So as I mentioned a moment ago, we want to be able to replace virtual sites with multiple time stepping. We still need to do some research to figure out what it's going to take to allow that. A really important suite of tasks that are important for the GROMACS developers, and hopefully will result in us having more time to work on features that are important to users, is some modularization of the core and encapsulation of the low-level layers of GROMACS. And this is actually related somewhat, or fairly strongly, I guess I could say, to the Python and C++ APIs that I talked about in the first third of my talk. So basically, we want it to be easier to compose the different modules, for the modules to be less dependent on each other, and for it to be easy to, maybe you could imagine saying, oh, GROMACS has this feature in the non-bonded force calculation, and LAMMPS has this feature in the listed forces, and so I want to use a GROMACS non-bonded calculator and a LAMPS listed forces calculator, and then I want to use the update code for GROMACS because that's nice and modular, and then I want to chain this all together in a nice workflow, and so this is something that we really hope to be making more and more progress on as time progresses, because we recognize that this is important for extending the scientific use cases, and at this point, even for being able to add new hardware support, it's very important that the core be more modular, because it gets more and more complicated as more and more things are having to be managed at a low level. So another thing, which I would say mostly actually exists, is having more extensible force calculation. So we have basically some functionality in GROMACS already that makes it easy to write a small amount of C++ code and inject new forces into GROMACS. And so this will be made even easier when we get better encapsulation of lower levels and better modularization of the core. I also mentioned a little bit about task parallelism and auto-tuning. So we really want to be able to just sort of automatically say, you asked for this to be run on the GPU and that to be run on the CPU and to only run one copy. We looked at your system and what you asked for, and we think you should actually just run 4 with this configuration. And so it would be really nice to have that sort of automatically be able to be decided, or at least to give you a strong hint that this is what you would want to do. And so this would be very useful, for instance, to allow ensemble strategies for free energy surfaces. So another thing that we would really like to provide, because we know it's a strong value to users, is modernized preparation and analysis tools. So in terms of the preparation tools, PDB to GMX we know can be a big hassle. There's a lot of corner cases in a PDB file, as I think I mentioned in response to one of the questions. And so this makes that code very brittle, very, very hard to update, basically. So we really like, for our own sake, as well as for the sake of our users, to have a, more modular approach there. But, we haven't made so much progress, although I can maybe say that Mblib having defined a new topology framework is, an important step in that direction, at least. And also that some work has been progressing on analysis tools. So we've been, in the past couple of years, continually hoping to get a replacement for TradConv. It unfortunately, has kept sort of slipping between the couch cushions, but we really hope that in the not too distant future we can get that. So I guess that's all I will say for today. So I want to thank everyone for taking some time to listen to me, and if people have any more questions, now's a good time.
Yeah, up to now there are, thank you, Joe. Up to now there are no questions on the live document, but maybe people can just raise the hand now and ask question.
Excuse me, Alison, I think there is a question which is not still answered in a live document, no? About MD simulation in DNA, but I'm not sure.
No, but that is not under GROMACS feature.
Oh, yes. So yes, right.
Yeah, so I'm just looking
Okay,
to the GROMACS feature. Thank you.
Okay.
Yeah. So
yeah, sorry. Yeah, this is related to the next. The next.
Yeah, and the next for the next one there are a couple of questions.
Yeah,
sure. Yeah, there are, but these are for the following lecture.
Lots of questions even before the lecture.
Yeah, and I think there are some answers also. Yeah. Already there. Yeah, and Yeah. So, and in the chat, so I would suggest if people want to raise hand, maybe if they have some question directly to Joe now.
Should have made a poll to the effect of like, was this talk relevant to your interests? Perhaps I mistargeted to the audience.
No, I think it will also be good to say how people want to contribute, if they want to contribute.
Yeah, that's a great question, actually. So yes, we are happy to get contributors. So there's a number of ways you can do that. I mean, so if you find a bug, for instance, you can report that on GitLab. If you have a cool new thing that you've developed, which you think is a useful feature that many other GROMACS users would want to use, you know, and it's been published and cited in the literature, you know, it's possible that the GROMACS team would be interested in having such a feature. And so basically the best way to go about trying to get that feature integrated is essentially to come to, so there's a mailing list called GMX developers. So you can sign up for this mailing list and learn about when we have our, every other Wednesday, we have a developer call where anyone who's doing GROMACS development can attend. And so, you know, on one of these calls, you can basically say, hey, you know, I've been working on this feature, you know, are you guys interested in it? And, you know, then there can be perhaps some coordination to figure out what the roadmap looks like to get the feature up to our code quality standards, and, you know, to maybe get it merged into GROMACS.
Maybe just ask a very, very short question. Could you elaborate a little bit on what you mean by task parallelism? Because you mentioned that it's involves GPU, so it's not really something beyond, let's say, or beyond OpenMP MPI, right? So it's taking account GPU. If you have a GPU, then you can parallelize.
So I would say there are two levels, basically, and I kind of slipped between the two levels. So of course, as you mentioned, there's this low level of having task parallelism, you know, across, you know, OpenMP threads and, you know, using coordinating GPUs with MPI and OpenMP threads. And so this is obviously very important. This is an active area of research in the HPC community. Unfortunately, most of that research is not really that applicable to GROMACS because the types of tasks in GROMACS tend to actually be much shorter than the types of tasks in other kinds of simulations. And so the task parallelism engines that people have been developing in the past few years don't, they're basically not applicable because the overhead is like on the order of our full step size. So, you know, it's an area of, you know, that we're greatly interested in this low level one, but it appears that for the time being, this is something we're going to have to mostly manage ourselves. And this is why I also mentioned that, you know, the sort of embarrassingly parallel task parallelism, which is just running multiple copies of the simulation, is something that we also want to focus on going forward because, you know, getting more flops out of your CPU or GPU is obviously very useful, but at the end of the day is maybe not the goal of scientists. You know, their goal is to answer scientific questions.
Yep. Thank you.
I just add some link in the chat for who is interested.
Yeah, I don't know if there are no other questions. I think we can, if you agree, we can wrap this session and have a lunch break, which will be a very late lunch for you in Stockholm, I guess, or unless I hope you have eaten already something. But yeah, but for us it's so we will then reconvene. Thank you.
Okay, thank you. So I'll try to share my screen, which initially sometimes give problems. Let's see if I can make that work. there? No.
Yes. I think you can see it.
Yes, but no, I hope the full screen. You can still see it?
Yes, yes.
Good. Okay. Then I can start.
Yes, I think so. Well, thank you.
Okay, so welcome to this afternoon session. So I'm Berk Hess. I've been working on GROMACS for more than 2 decades by now. Responsible for a lot of the parallelization, the fast algorithms, and also since some time I've been working on the accelerated weight histogram method to accelerate sampling, which I'll tell you about today, what it's how it works and what its advantages are, and a bit on how to use it, but tomorrow you'll hear more about that during the tutorial on this. Okay, so the outline for this presentation is first an introduction to general sampling issues and how does the method work, how to use it, and then I'll show a few examples. And then I also very quickly show how to use this for alchemical transformations. There's not much time for that, but there's another webinar, or there's a webinar on BioExcel that you can listen to know more about that. And then there should be some time for questions. Okay, so first the references and to show who actually did the, most of the work here. So there's a list of manuscripts here, actually not the original manuscript by Jaak Litmar, who was not mentioned here. He didn't do any coding, but he developed the original accelerated weight histogram method, which then my PhD student Viveka Lindahl, who's now graduated, transformed and adapted for molecular simulations. And recently, Magnus Lundborg adapted it to work for alchemical transformations. So that's been included in the latest GROMACS release. So here you can find all the scientific details and the details on the methods and all the formulas, which I will not show much of in this talk since the time is too short. Okay, so the general issue here then is that, as probably most of you are aware of, is that the energy landscapes of biomolecules are usually high dimensional, and they're often quite rough. So it's difficult to understand how these landscapes look like, also because you can't judge that from just looking at a molecule. But you'll see if you try to sample this that it's often quite difficult. So typical situations could be that, for instance, you know the beginning and the end states of two different conformations, for instance, of a molecule you're interested in, and you wonder what are the paths connecting these and what are the free energy barriers, or what's the free energy difference between these two states. But you could be in a more difficult situation where, for instance, you only know the beginning state of the molecule and you know that the molecule needs to do something to turn into an active state or to bind something, for instance. So that's even a more difficult problem. So in general, I mean, there are a few completely unsupervised methods, but usually you need to come up with a reaction coordinates. Many methods require this, and the more powerful methods do. So then that's the first thing you need. You need some way to describe in which direction the system needs to go. So here there's a picture, a schematic picture of a free energy landscape that somebody just drew out of imagination. But you see here 2 minima, and for instance, you could be interested in to know how the system goes from the one purple minimum to the other, and then there could be multiple pathways. So you could, of course, there are different methods for pushing the system from one side to the other. There's umbrella sampling if you actually already have a path, but very often you don't have a path at all to start with. If you have a reaction coordinate, then there's several methods you could use, and one of them is the method I'll present now. So yeah, if we look at go back to molecular dynamics and see what the situation is. So it's often that, especially in biomolecules, interesting events happen on a microsecond time scale. Thus, we need, as been discussed today, we need billions of time steps of around 2 femtoseconds. So that's a lot of work you're doing. But the event itself is often quite fast. So actually, when a transition occurs, this might, well, it might not happen in picoseconds or so, but maybe some nanoseconds, some tens of nanoseconds. So you actually, most of the time in simulation, as I'll show on the next slide, you're often waiting. So you would like to use, you can use then many independent simulations, for instance, to sample this, the events are fast, as long as you sample enough events. So then you need to do this, you need to find ways to smartly bias your simulations to get more events out of this, because just running more simulations will not help. I mean, they'll, on average, they'll wait as long as originally. Thus, I mean, what you would like to achieve here is a more efficient use of compute time and a shorter time to solution. I mean, these are both advantageous, right? So you need to ask for less computer time, or need to buy less expensive computers, use less electricity, and also you get your answer quicker. So that's what we all would like to have. So here's a schematic of this. I mean, here's what could happen. And here we just have a free energy. So this is a toy system that my PhD student made. So this is just a Brownian motion in a double well potential, and you see that you need to wait very long. So I mean, if you know your statistical mechanics, then you know that at some point this red degree of freedom, this red ball, will move to the other side and sample the other side. But that can take, well, the probability, or the time scale at which this happens goes up exponentially with the height of the barrier. So of course, if you know how this landscape looks like, then you can use a bias potential to remove the barrier. So that's the way that many of these methods work, including the AWH method. So if I can figure out a bias potential, this blue potential, that's the negative of the free energy we have here of this landscape, you could flatten it out. So you get this flat line. Then of course the particle will move uniformly, or it will distribute uniformly. It will move quite quickly. It will just diffuse over this flat landscape. So that's what you would like to do. But the issue here is that the potential, or this free energy you're after, this blue bias, is exactly equal to the free energy, which is nearly always the unknown that you're interested in. You want to compute this unknown free energy, and you need that to bias the simulation. So that's what the usual problem is here. So if you could, there are approximate methods that can somehow get rid of some of this barrier. That already helps a lot, since the time scales go down exponentially then, but you would like to systematically do this. So how to do this then is that you need to have an iterative solver, because your potential or free energy is both the input and the output of the method. So that means you need to solve this into some iterative fashion. There's some solvers available. So metadynamics is a very well-known one. There's adaptive biasing force. There's the accelerated weight histogram method, as I'll present here. So these methods are all fundamentally not so different from one another. They're quite similar, but they differ in the details, how they handle the statistical mechanics and how they're formulated. Okay, so what's particular about the accelerated weight histogram method? So in this method, there's the target distribution as a central quantity. So that means that the method works as the fundamental way the method works is that it tries to bias the sampling towards a distribution that you set, which is often flat, but could be an arbitrary distribution that the user chooses. So you know what you're after in the sense of the target distribution, not in terms of the free energies, and that's still unknown, but at least you know what distribution you should get out. That's a very important aspect here. So many other methods like metadynamics, they have a target distribution which depends on the unknown free energy. So you don't know, if you get a distribution, you don't know exactly what you're at, whereas here, if you reach the target distribution, you know your sampling is quite good. So then the second point is that this distribution can be chosen freely. So this is also quite nice, since then you can choose where you want to sample more or less, which if you don't know anything, you can choose flat, but we even have better ways for that, which I think I won't go into here today. And it could depend on the free energy, like in, for instance, metadynamics, but it doesn't have to. Then another practically very useful aspect is that it has an initial exponential convergence. So initially the error converges exponentially, which if you know statistical mechanics, that's impossible in the long run, since in the sampling should always go, the error should go down with the square root of the number of samples in the end. So that's what happens in the final phase. But if the errors are larger than the thermal energy, than KT, then you get exponential convergence. And this is automatically controlled. So this is very nice that you get, even if the errors initially are very big, those go down exponentially. And then later you go, as the errors get smaller, you go to the expected 1 over square root number of samples error. And this is controlled through one uncritical convergence parameter, which is also nice. So you don't need to tweak a lot with parameters here. So that's I said already now in advance, the important aspects and properties. So now I'll go into detail and show or give an illustration of how this works in practice. So what we do is we start out with some initial bias that we put into the system, which initially is flat. If you don't know anything, or if you know something, you can put that in. Then you run a simulation, which is then biased. So you get samples out of this, of the distribution along the direction coordinate. Then from this, you can estimate the actual distribution, since you assume that you should get the target distribution that you put in, but you didn't get that. You get this green curve, whereas you wanted, for instance, flat. So from that, from this difference, you can assume, or you can, if you assume that this difference is due to the underlying free energy landscape, you can compute what free energy there's acting to give this distribution, this green distribution of samples instead of what you expected. So you can apply a correction for that, since you have more information now of how the free energy looks like. So you can update the bias, you get a new bias, and then you can run another bias simulation. And this goes around in circles. So strictly speaking, one would need to run separate or long enough simulations that you cover the whole reaction coordinate range. But in practice, you can do this very frequently. So we do this circle every, well, it depends on how you set your parameters, every 1,000 steps or so. So we update continuously, and that works fine in practice. Okay, so to show, this is, I think, the only actual formula I have that shows how the update size changes. So here are in the schematic diagram are the steps given again, where you have the free energy estimates F0, F1, and Fn plus 1, and so on. And then you have the change in weights that you observe here, and those go into computing a new free energy, a new bias as well. So how the free energy estimate is updated is shown here in this formula. So you have a delta Fn, so that's the change in free energy as a function of your reaction coordinate lambda, and that is equal to minus the log of 1 plus, and then here is the difference of the collected samples. So this is delta W, that's the samples collected during the last phase, divided by the prior number of samples you have. So that's how much information you have times the target distribution. So your distribution that you want to have is pi of lambda, which is often flat, but could be something different. And this collected samples should slowly converge towards that. So if they match, then actually there's no update at all, or well, it's a constant everywhere, it doesn't change. But if it differs, then you can see that this update size roughly goes as 1 over n down. So that's what you would expect. So that means the error goes down as 1 over square root n number of samples. If you add random and non-correlated corrections here. So this update behaves as it should, and you see it's actually, I mean, it's, yeah, you can't right away understand probably this whole formula, but it's not that complicated either. Then there's a lot of other math coming into showing how the method works, and that's consistent, but this is still relatively simple. So yeah, the free energy gets corrected with, as I showed in the previous picture, the observed samples versus the target distribution that you're after. Okay, so how does this actually work? How does IWH do this? So what we initially did is we used a harmonic umbrella potential, and we moved using Monte Carlo moves. So that's a bit similar to umbrella sampling, but then the umbrella moves. But that's a bit annoying because you have Monte Carlo, you have jumping umbrellas which add noise. So what we've done instead is to use a Boltzmann inversion of the sum of these biases that we have here. So you get a convolution of Gaussians. So that's the inverse of these umbrellas. So that creates a smooth biasing potential. So in the end, the statistical mechanics of these two methods is exactly the same. But now you have a smooth potential that you move on, which is much nicer. So now you just do plain MD. There's no Monte Carlo moves. There's no randomness there. So this is a much more elegant way of handling this. Then how these Gaussians are put onto the system is through a regular grid, considering, and because the Gaussians, they decay quickly, you only need to consider close neighbors. So this is an advantage compared to other methods like metadynamics, where you have Gaussians which are not distributed on a regular grid, because here you know how many Gaussians to take into account, and you can pre-compute many things. So this also means that there's no higher cost when using a fine grid here, because that means that you there are many more points, but you always only need to consider a very small neighborhood. So you can take an extremely fine grid, or that's actually set automatically through the steepness of these umbrella potentials, which controls the width of the Gaussians. So this is nice. So you don't need to worry about efficiency or cost when choosing your force constant in this method. You can have a detailed landscape anyhow. Okay, so then a picture of how this works for the toy system again. So here we have the same double well potential, and then we have this red particle, and you have the initial free energy estimate, which is this blue line. And then we can see what happens here if we make it move. So you see here that you get a bias quickly built up in the minimum where it starts, and then the system moves to the other minimum, and then starts correcting there. So you see that there are local updates, and you see as the particles on one side, you see the other side going up slowly. And you see the updates get smaller and smaller. So this is, I think, all still in the initial phase, because there's these factors where we have. I'll soon explain how that works. So we can run it again. It starts out on one side, and then because the free energy estimate gets pretty close, the system quickly jumps to the other side, and then it starts converging towards the final free energy here. So this is how the method works. So this is in a simple one-dimensional toy system, but it's fundamentally, it's not different in a complicated protein, since you just see the reaction coordinate. Of course, the potential can look very different, and the system can be 1,000 times slower to simulate, but from the point of view of AWH, there's no difference between such systems. Okay, so then I can explain how this exponential linear convergence works. So what we do here is that in the initial stage, we have two stages. We have an initial stage and a final stage. In the initial stage, we keep the update size constant. So this is actually inconsistent with the formula. Let's see if we can go back to the slide of the formula. So here, the formula for updating for the free energy shows that the updates go down as the number of samples go down. So if you've already collected a lot of information, that means that if you add one more point, that weighs less than if you have had only 1 point and add a second one, and then you double the information. Whereas if you have 1,000 points and you add one, then you have little extra information. So the update size should go down all the time. But actually, initially we keep it constant because there we don't know so much. So and that also makes for a way for us to have this exponential linear convergence. And then if we what's called cover the system, that happens at these crosses. So that's if we went from one side of the reaction coordinate to the other, so we visited both ends, then we halve the update size. Yeah, and then we again wait until the system crosses to the other side, where this is a green cross, and we halve the update size again. And we do this until we come to the point where we would exceed the final weight as computed by the formula before. So there's actually a natural point for exiting this procedure. When the weights, they would be inconsistent with the formula I showed before. So then the system has automatically found the correct update size, and also related to that somehow the correct, some kind of error estimate which you can't quantify easily, but that's related to that. So this means that the system can very quickly set the update size correctly in logarithmic time. As a function of the initial error. So even if the errors initially are 10 KT or 20 KT, 20 thermal units, you can very quickly correct for those errors and build up an initial bias, which is quite good. And then after that, the weight goes down as 1 over 1 over time, 1 over number of samples, as you would expect, according to statistical mechanics. So this is an extremely powerful feature of the method, which makes it both fast and very easy to use, since this means that the initial how you set this initial update size is not very critical. If I have it too large by a factor of 2, I don't need to wait twice as long. I just need to wait one of these steps, one of these crossings extra. So that's has quite little effect on the convergence speed. So the only issue there is if I make it too large, you might pull the system apart, or if I make it too low, you have to wait a very long time. But if you're in a reasonable regime, it works fine. Yeah, the update size, then you can look at the sample weight. So the sample weights are how much each sample weighs there, which in the end should be equal. So if I sample in equilibrium, then each point I sample, each point I visit should weigh equally. That's what happens in the end. But you see here that due to this exponential weighting scheme, exponential update size scheme, you're actually weighting down or weighting up the points initially, because you're not decreasing the update size. But then once you have the update size, they get weighted down. But you see that in the end, the initial points, they weigh very little, the initial sample points, which is good because those were sampled with a high biasing and a not very correct biasing potential. So you don't want a large weight of those. You could also cut this off of the statistics, but in the end, so this is a log scale. Oh, I didn't put numbers here, but those are weighted away completely. So they're anyhow, they don't contribute much to the final answer you get. So that's also nice. You see also that again that here, I mean, just like in this picture, I mean the weight here should be higher than the final weight. So that's again what set this cutoff at the blue spot where the initial phase exits and you go to the final phase. Okay, so that's it for the basics of the method. So that's I'll refer to the papers if you want to read more about that, or the GROMACS manuals as a bit of that. So now I'll show an example application. So this is about DNA base pair opening. So this is a nice case because it's relatively easy to see what happens, but also there's large timescales involved. So if you look experimentally on what happens, so you have a DNA strand which is usually all paired, which actually is biologically is not an interesting state except for storage. So if somehow information needs to be read off of DNA or something needs to happen to it, it needs to open up, because otherwise the base pairs are inaccessible to anything wanting to either inspect or to correct something here. So all the interesting things happen when the base pairs open in some way. So the simplest event is one base pair flipping out, as is shown here on the right side. So this is a very important event since all the biologically relevant things happen, like repair or reading in an open state. So if you look at an experiment, you can see that base pairs open roughly once per millisecond, which is very infrequent. So that's something you can't reach with simulations as of yet, at least. But then if it's open, it closes in about 10 to the 4 times per millisecond. So that's 10,000 times faster. Yeah, so it's that if you know your statistical mechanics, you can see then it's open only 10 to the -4 fraction of the time. Huh? So that's very infrequent. So this means experimentally you can't see any of these states except through NMR, which sees exchange happening on atoms that are no longer buried inside the double strand. So this is a nice showcase here, or a convenient example case, because you can see here that, I mean, this is unreachable through molecular simulation. Plus, there's a very high free energy difference here. So this will be KT log 10 to the power 4. So that's pretty large. Sorry. Yeah. So what we do here is we need a reaction coordinate first to act upon. So in this case, we chose as the distance between these 2 nitrogens here in this particular base pair. We try multiple base pairs, but for this particular case, I mean, all of them are between heavy atoms like this. And it's only the distance. So you can see here if it's short, then it's paired, because if it has the right hydrogen, it must have the right hydrogen bonding partner if it's very short. And if it's longer, it will be open. So this is already somewhat different from previous studies in literature, which often use dihedral angles or angles between these base pairs. But that means that you need to distinguish between four different modes, because the one can swing to the left or to the right or to the minor and the major groove, and the other one as well. So you have 4 different opening modes in principle, 2 times 2. But here with this distance, the system simply chooses what it prefers. So that's also nice. So that's because AWH, it samples, unlike, for instance, umbrella sampling, it samples back and forward. So you don't have to choose these options. The system will choose the one with the lowest free energy for you. So that's an advantage of having a dynamic method, which, for instance, metadynamics also is, versus a static method like umbrella sampling, where you would have to fix the path. So you get what you chose as an initial opening mode. So here we get all modes that are relevant automatically. Okay, so we've now defined this distance, which in GROMACS you do through the pull code, and then we can have AWH act on this. So yeah, just to show what the pull options are for those people who are not familiar with this, this is rather simple. So you need to say that you want the pull code on. So you say pull is yes. Then you say you want 2 groups, which in this case is I called res ID 8 and res ID 33, but of course it's this atom and this atom that needs to be in here, these 2 atoms. And then I define one reaction coordinate. Sorry, I say I want 1. I take the distance, and then I take the distance between these 2 groups that I just defined, number 1 and 2. And then to make AWH work, so normally this you would have a potential on this, which by default is a harmonic potential. But here we say, as a coordinate type, we want external potential. So there's an external provider of the potential, as we call it, and we name this external potential provider. We say it's AWH. So now AWH will supply potential and forces to act between these 2 groups here, these 2 atoms, and the distance between these 2 atoms. That's relatively simple. Then you need the AWH parameters here as well. So you need to turn on AWH. We want to have 1 bias. So in this case, there's 1. You can have multiple independent biases active. I mean, in case you would want to have independent biasing of multiple things. Here we have 1 bias, we have 1 dimension we act upon, and that's this. The coordinate index indicates that you want to act on this coordinate 1 here. So that's this index 1. So that tells you that it should act on that. Then what I need to set is I need to set a start and an end, because what the AWH method does is it works toward a target distribution, which by default is flat. So you need to say how far you want to go, because otherwise, you could have infinite, maybe theoretically, but no, then the target distribution would be 0 in the end. So you need to have an extent you act upon. Oh, sorry. Then we set the force constant here. So the force constant here is very high. So this is 128,000, kilojoule per mole per nanometer squared. And that's because there are high forces here. So this will lead to a very sharp umbrella, narrow Gaussians and a fine grid. But as we said, it's not an issue. So I think this is about the limit for the time step in this case. So if you make it much higher, then you might get integration problems. But this is not a problem for the efficiency of the method. And then, I don't know if I show that later, how we set the initial error. The initial error is set by 2 numbers. So by the diffusion constant and error and AWH error in it. So these 2 numbers go into 1 final number. These are not independent parameters. So this gives you, the initial error is a rough error estimate of the initial error, which I set to 5. I think units per mole, could maybe be a bit higher. And the diffusion gives a rough idea of how fast the reaction coordinate moves. But it's not very critical, as I said, because the initial update size is not so critical. So that's okay. And then here I also added, for the case I have multiple simulations working together, which I'll show later, that you can have multiple walkers contribute to the same bias. I'll show that in action later. So you need to set a few parameters for that. Okay, so that's not that complicated. There are some parameters, but most of them you can argue about. You need to guess a bit about the diffusion and the error in it, but that's not too critical. So this way you set something up. So then, here's the error formula. So I choose these 2 parameters, but in the end, there's the initial update size only, and this goes, the initial update size, or the 1 over the, yeah, that's 1 over the number of samples, exactly, its initial update size, is proportional to the diffusion times the error squared. So this is the quantity that's used. So this is not an equals to, because yeah, it's a bit complicated here. So you need to have some order of magnitude of this. So you see, you can increase one and decrease the other, and you get the same initial error. So, but especially the same initial update size. But in particular, the error goes in with the square. So this weighs a bit more here, but that's how it works. Okay, so yeah, and as I said before, if you choose these parameters far too large, then you get slow convergence. So because the updates are going to be very small, and if you choose them too small, then the system at some point might be pulled apart. So, but you'll notice that, of course, when your simulation crashes, you'll know that you chose it too small. Then you can choose it a bit larger. But it's better to try a few things, because you might not notice that you have chosen too large parameters and you get slow convergence. I mean, then it might be difficult to notice initially. So better to try a few values to see if you can get it faster. But it's not very critical. So there are several orders of magnitude where it works fine. Okay, then we can look at what comes out of the method. So here's an example output of MD run, where I now show all the outputs that comes out of AWH. So usually the main thing of interest is the potential mean force, the free energy along the direction coordinate. That's the black curve. So this is for the base pair opening in this case. I showed this. So there's the closed base pair and the open base pair here. And you see they differ about what is it, 12 kilojoules per mole, something of that order, which I think roughly matches the experimental, the free energy difference that you would compute from the experimental numbers. Then there's the coordinate bias. So that's actually the bias applied to the system. So that's very similar to the potential mean force, as you see, but because of the umbrella potential, which is convoluted, it's slightly less sharp. So you see it smoothed out a bit that you get. So the output automatically deconvolutes the bias. So you get the actual BMF without the umbrella. So even if the umbrella is, here it's quite tight, but if the umbrella is weak, you might get smoothed out BMF, but that's automatically accounted for in the output. Then you can see the coordinate distribution, the green curve. So that's the green curve is here. So, and the target is the orange. So here we targeted flat. So there's this flat orange distribution, and see that we have oversampled a bit the green in the minimum here, and we undersampled a bit outside. So there's some, it hasn't fully converged yet here in this case, but it's pretty good, the target distribution. So this doesn't mean that the errors of this size, the error in the BMF is lower than the deviation here in this distribution. I mean, the method, when computing the free energy, it takes into account that it has the green curve differs from the orange curve. So that's not an issue. There's a reference value distribution. So that's where the umbrella is put, which differs again because of the same reason that the red and the black curve differ, because of the umbrella coupling. So you see it's differs slightly from the green. You see actually at the edge, you see here that the umbrella is not strong enough to pull against this very tight, this very high wall here. So you see that you move the center of the umbrella out with the blue curve, but then the green doesn't keep up. There the force constant needs to be higher, but we don't care at this wall what the values are. Then finally, there's something which we call the friction metric, which I don't explain here in this presentation due to lack of time, but this tells you how high the friction is, or how difficult it is to sample along the direction coordinate. And this is very useful, since it can give you insight in what's going on in the system. So here you actually see that the friction metric is quite low in the minimum around here, and it's also quite low outside. There's a peak here, and the peak here is approximately where also the peak and the potential mean force is in this case. And that's because, let's see if we can go back to a picture. That's because the difficult part in sampling this reaction coordinate is where you have to find the correct hydrogen bonding partners. Yeah, so you can imagine if it's partnered or nearly partnered, then the system has no problem moving back and forward along this green distance. Also, if it's completely open, like here, well, here it's hydrogen bonded, but if it's a bit further open, then the system just wiggles around without much trouble. But the problem is, of course, finding the right partners here completely, and that's what this peak in this metric shows you. So this is very useful because it can actually give you insight in where the difficult processes happen in your physically difficult process in your system. So this can give you insight in what's going on. What you would actually want to do is you want to sample according to the metric given by this distribution. Oh, this is actually a friction metric, right? So this is, I think it's a metric. So you want to sample according to the square root of this, not a flat distribution, because this tells you how difficult it is to sample at different points. So that's what we should actually do, but we haven't automated that yet. It would be nice to say I want to sample according to the friction metric. Okay, so then here's some examples of what can go wrong. So here I think I simulate with a smaller force constant for the umbrella, and then you can see that you get the deviation. So you get the coordinate distribution differs from the reference value distribution because the system can't keep up with the umbrella. So that's quite typical errors that you get. Also here you see that there's the distributions are very much off from the target. So that's in the initial phase. So these are things you can easily observe in your results. So any kind of problems can usually be seen, in particular because you know what target distribution you want. So anything that deviates is not correct. So that's a very nice property of the method. Yeah, so here's some results. So here we look at different base pairs in different colors for two different force fields, and you see that you get different curves. You roughly see the errors as the width of these bands. So this works well, and you can get accurate results, and you can see difference between force fields, and you can see differences between different base pairs types. Okay, so then a point I alluded to is that you can use Ensembl Parallelism. So there's no reason to limit the sampling in this sampling phase to a single simulation. So you can have multiple simulations contributing to the same bias and the same weight collection. So we can run an ensemble of multiple simulations, and they can run fully independently apart from that. They need to add to the same bias and have the same weight histogram. So then the question is, of course, how many copies can we run? Or yeah, how does the convergence depend on the number of copies, since you would expect that there's at some point there's a limit. So here's an example of the toy potential again with now multiple walkers, which I always forget how many there are in this movie because they move too fast. I always forget it's 4 or 8. But you see now that converges much faster. So this movie runs at the same simulation speed as the other movie. So you see now that because now you can have different walkers work on different parts of the landscape. So it's not that it's stuck on one side for a very long time. And it would get even better if you start the walkers distributed uniformly, which I think I didn't do in this movie. Let's check. Oh, sorry. No, they started at one point, right? So if they would start distributed, it would go even faster. So you see here that I mean, you can have multiple simulations contribute, in principle, as many as you would like to the same bias. So it gives you a nice way of parallelizing, because now you can just throw in more hardware by using more simulations. Very convenient, and they need to exchange information only very infrequently when they need to update the bias and get the new bias from the other rank. So it's recoupling, so it's also efficient on communication. But then the question is, how does this go convergence-wise? So that's what you would like to know. So here's examples of the error as a function of simulation time for different walkers. Oh, sorry. So here's one walker, is the black line. So you see it's initially very noisy, and then it's in the end it should go down to this 1 over square root time curve, this dashed curve that I have here, which they roughly do. But then there's a very surprising thing one can notice here, is that if I go from 1 to 2 walkers, the error goes down by a factor 4. So the error gets, at the same time, is a factor 4 smaller here. Or sorry, it's a factor 2 smaller. The variance is a factor 4 smaller. So you would expect it to go down by a factor square root 2, but it actually goes down by a factor 2 if I go from 1 to 2. Then after that, it goes down as you expect. So the variance or the error squared goes down as the number of simulations. So here from the red to the green, it goes down by square root 2, the error as you would expect, and so on. And then, but still, you see that still at 32 walkers, there's still an improvement over 16. I don't know if you actually run 64, but I think the limit is somewhere there. So this means that you can scale to 32 walkers here and actually run more efficiently than running 32 times a single walker. So you get not only an improvement in time to solution, because you can run all these things at the same time, but you actually get an improvement in overall computational time used because of the superscaling from going from 1 to 2 walkers, which I think we understand because the system in 1 minimum, I mean, if you go back to, I mean, the original movie in 1 minimum, it's stuck on one side, and then this 1 walker needs to go to the other side to do some, to lower this minimum and then go back again. Whereas if multiple, you don't have this sticking issue anymore. So that's where you think this large effect comes from. So this means that it's almost always advantageous to run at least 2 walkers, and certainly 4 should also be fine. And in many cases, you can go up to many more. So this is a good advice to run more. So yeah, so here we did a showcase for BioXL is where we, without bias sharing, we could go time to solution for 20 base pairs on bits stained in CSCS in Switzerland with P100, NVIDIA P100 GPUs. We could get to, in 34 hours, we could get the answer for all these cases like we did in the paper. And with bias sharing, we could get this time down to 1 hour if we ran 32 walkers. The efficiency goes down a bit though, so the efficiency is still very good at 16 walkers, but you see the curve here that gets a bit flatter. So if you care about not wasting too much resources, you would do that. So this is a very nice that you can parallelize in this way. So you can, and you have more scaling, and you get your answer much faster. Okay, so then we can also do this in 2D. So I won't spend too much time on this because of I want to also talk a bit about alchemical transformations, but AWH is not limited to a single dimension. You can have multiple. So here's again for this DNA base pairing, we can have base pair opening. We can add a second reaction coordinate, which in this case is between the mis hydrogen bonded pair, which is this state here. So now you can have 2 reaction coordinates, the original one along X and the second one along Y. So that works fine. It can sample the whole landscape. But actually you see the landscape is relatively one-dimensional. I mean, it's the second coordinate doesn't add too much in this case, but it shows that the method works. But you can see the metric here. So again, the metric shown in 2D, you see that there's a narrow wall here of where the metric is high, which again, where the hydrogen bonding partners need to be found. But this shows one useful feature is that we can have a cutoff in free energy on to have the target distribution level off, because if you were in multiple dimensions, as you see already in 2, I mean, it would be difficult to sample this whole landscape because you get unphysical states. You can't have both distances very small, for instance. Yeah, so there are unphysical states here which are not interested in sampling in, which might pull the system apart. So for that, it's extremely useful to have a cutoff. So in this case, we set the cutoff to, what is it here? Maybe 20 kilojoules per mole, I think so, yeah. So then the system, the target distribution level goes to 0 smoothly after that. So then you avoid uninteresting regions and you avoid the system being destroyed and spending a lot of time there. So that's very useful. Okay. Yeah, another example here is aquaporin. So here we look at water permeation versus ammonia permeation. So we can look, we have the direction coordinate, the z distance of a water or ammonia molecule through this protein where there are 4 channels here. So again, this works very, very nicely. So it's a rather slow process, but you can sample, and then you also get conformational change of the protein in there, because the protein might change a bit over time. So if there's slow modes in there, you get those correct as well if you sample long enough. So you can see here, we can see differences between water and ammonia, and we can see in different force fields, different results. So unfortunately, the force fields are not perfect yet. So either one of the 2 is correct or they're both incorrect. That's to be seen. But yeah, you can think of many different direction coordinates, obviously. So now in GROMACS 2022, which will soon release, there will soon be a beta, and the release will be in January 2022. We have a new transformation pool coordinate type. So this adds a lot of new options, because then one can transform with arbitrary mathematical formulas reaction coordinates you already have, pool coordinates. So this means that I can, for instance, have a contact coordinate which counts high if it's close and low if it's far away, or you can have combinations, linear or non-linear, of multiple reaction coordinates of multiple distances, for instance, or angles. So this makes the pool code enormously more powerful to create complex reaction coordinates, because you can just type the formula you want and have it act on multiple multiple pool coordinates, or multiple other of these coordinates also, of these transformation coordinates. So this makes it much more versatile. Okay, so this was the part on physical reaction coordinates, where I've shown that it's hopefully shown that the method is very robust. You can choose your target distribution freely. You can use, there's only a single parameter that controls convergence, which is also nice. This parameter is not very sensitive. You can have different dimensionalities. You can have multiple walkers. It works efficiently in parallel, which is also nice. So I think we now have very powerful machinery if you have a reaction coordinate that can sample efficiently along that. I don't know if there's much more gain to be had there. But still, the problem of sampling biomolecules is not trivial because you still need to come up with good reaction coordinates. So I haven't discussed that here, but that's off topic for this talk. But that's the hard part, is coming up with good reaction coordinates. But if you have one, then I think we have a very good method that can sample them. Okay, then quickly I'll show AWH applied to alchemical free energy calculations. So up to now it was physical reaction coordinates, so distances, angles, and so on. But actually, a large class of free energy calculations are of alchemical type, where you want to, for instance, do solvation free energy. How much free energy does it cost or gain to solvate a solute in solvent, for instance, which you could do through a physical pathway, but you usually do through alchemical coupling and decoupling of the solute. Or, for instance, binding studies where you want to know how two different inhibitors bind to a protein, which you can draw thermodynamic cycles, and you can compute, for instance, if I mutate the inhibitor bound to the protein and bound in a solution, then you can have a delta G, for instance, of how much better inhibitor I prime is than I. So these are things where you would normally do standard free energy calculations, for instance, now with the Bennett acceptance ratio method, the bar method, which is the standard. So you run simulations at different values of what's called the coupling parameter. So you couple the system, you add to your Hamiltonian a coupling parameter lambda, which at lambda is 0, it corresponds to state A, and at lambda is 1, it corresponds to state B. So then you need to introduce some dependence. And what you would normally do nowadays is you would run simulations at multiple different values of lambda, and then, well, you wouldn't integrate, you would use bar. I have the integral here, but that's the formal free energy if you do it continuously, but in practice you would do that with bar nowadays. But that means you have to choose many of these lambda states. You have to choose parameters, run individual simulations, and process them. But what you're actually doing here is having a reaction coordinate lambda, and you're trying to map between one part of phase space where the system samples, for instance, lambda 0, this red area, and at lambda 1, the blue area, and trying to connect them through reaction coordinates. You need to find a good path, of course, but again, this is very much like what AWH does. So this, if we can, you can say lambda is just a reaction coordinate, and then we can apply AWH to this reaction coordinate as to any others. Yeah, so that's what we've done, or that's what Magnus has implemented in GROMACS, and this turns actually out to be pretty efficient. So in this case, you need to say, you need to set the AWH potential. We have an umbrella potential. You have a coordinate provider there, which is called now fab lambda, and then we have a start and an end, which are the usually 0 and 1, the end states of your alchemical transformation. You again need a diffusion constant, which again should be as high as possible to make things move, which goes together with the error as before. Nothing different there. And there's this equilibrate histogram option, which I haven't discussed before. That's a detail important if you have multiple walkers to make sure that they sample the whole landscape. And again, the parallelization can be chosen freely with multiple walkers. So this is really nice. So now you're not linked as with the standard methods to having as many simulations as you have lambda points. Now you can choose as many walkers as you want. And this works very nicely. So this works, let's see, do I have the... yeah, so this gives, as for the physical coordinates, it's not very sensitive to the parameters, to the distribution and number of lambda states, so you can choose enough here. So you don't limit it by, in the standard schemes, you want to have as few as possible because it gets more expensive, but here you can choose as many as you want, again, because the system moves along lambda, so it's not fixed. So, I mean, the AWH moves back and forward, so you don't fix the system. It converges at least as quickly, we show in our paper, as equilibrium simulation, so it seems to be a bit faster, but we need more cases to to say really if it works generally better. Yeah, it's trivially parallelized, as I said, by using multiple walkers. And it can also be combined with other AWH reaction coordinates. Actually, Magnus implemented this also to combine with pulling through the system, because he's interested in how molecules behave in a matrix of skin in that case. So this, we think, is a very promising method. So it's relatively new, so we haven't fully tested it against, or many cases, against the standard methodology. But for the case we show in the paper, it works as good or slightly better. So overall conclusions then. So I think, yeah, we have a very robust and accelerated sampling method here. There's only one parameter that controls convergence, although it's given by 2 MDP options, and it's not very sensitive. So we have 1D, 2D, more D, but it gets difficult to sample. So 1D and 2D are the most important, and our lambda reaction coordinates. We have, as I showed, multiple walkers, which is very nice for the parallelization and works very efficiently. And then if you would like to know more, there's the papers I showed in the beginning, and there's the GROMACS manual, but there's 2 webinars on at bioexcel.eu, one on the AWH for physical reaction coordinates, which is where a large part of this presentation came from. And there's another one on by Magnus and me on the AWH applied to alchemical transformations. And finally, there's a nice tutorial which runs through Python notebooks in the cloud, which we recently set up. For AWH, there's one here available at this address. But if you just think, if you Google AWH tutorial, it's probably one of the first hits. That's what I wanted to say about AWH. There will be the tutorial tomorrow. I think there's time for questions.
Great, thanks, Berk. So there are a couple of questions from the living document. So one of them is, how can we ensure that an artificial, not biologically relevant minimum of energy the system finds isn't blocking the system from accessing confirmations that would represent experimental results?
So with that, I presume it's meant that you have defects in the force field which cause some artificial state to be low in free energy, or maybe to be a local minimum, or maybe of course you could also have local minima which are not, which you get stuck in. But then I think that's a problem that's a general issue, not particular to AWH, but you of course might encounter that. So the thing here is at least that you set up your simulation, you run it, and it either converges or it doesn't work. So that's good. So if it converges, then you know what the free energy is and you have it. And if it doesn't work, then then you'll see that distributions won't work. You can't get to where you want. So that's one thing. So then either you get to where you want or you don't. So if you don't, then you need to do something. So you need to either change the reaction coordinate or change the range. So I think there's not much more than one can do than that, is to ensure that you that you either get a converged answer or you get to say that it can't actually reach convergence, and you need to do something. So that gives you at least handles on tackling this. But I think there's no magic solution to that apart from sampling more, what you'll need to do.
Okay, another question is whether running multiple walkers counts as replicates, or are the biases the same and we can't consider them to be independent replicates?
No, the whole point is that they're not independent, because that's what gives you the increased sampling rate, and that's what gives you the superlinear acceleration. So if they would be independent, then they behave independent. So they're not. So that's good, because the convergence and the time to solution goes down. So the time to solution goes down from 1 to 2 by a factor of 4, which is great. But that of course means that it's more difficult to estimate error. So that's something I should have mentioned that. I think I forgot to mention that on these slides. So that's actually, that makes it more difficult to estimate error. So for that, we do recommend independent replicates. So you could run, for instance, 4 sets with each 8 walkers or so, but 4 independent ones of those. So you can have some error estimate. So that's always useful to actually have some completely independent data, because otherwise estimating errors is difficult, or can be difficult. You can have some rough idea, but you can't have exact numbers for that.
Okay, I think that was all the questions. So thanks. All right, so in terms of the schedule, it looks like
we are now going to the talk with by Professor Miguel Masqueira. I think it's it. So now the idea is to maybe change a little bit from the technical point of view, more for application point of view. So Miguel is going to show his work that is being developed in Faculty of Science in Lisbon on pKa and application to proteins using GROMACS.
Hi, everybody. Can you hear me?
Yes.
So, all good. Let me start by sharing my screen. Try to share a virtual machine. It always has some, yeah, I think you're seeing my Windows machine, right? So if I slideshow it, you can see it. Can you confirm? No one confirms it.
Yes, Miguel, we are seeing it.
Thanks. Nice. Okay. So so this is a GROMACS workshop, kind of. So I'm assuming that everybody's learning how to do molecular dynamic simulations, and I'm lucky not being the first one in the morning, because then everybody already got a taste of it. The ones that have some experience will not need anything special to follow my slides. All the others that just started today with molecular dynamics, at least they sense the problem. That will be, even though they cannot see right away the solution, they know that there is a problem. And what is the problem? Problem is called pH when you are running molecular dynamic simulations. So the moment you start dealing with pH, which most often you don't, you end up in these two different worlds. So there is the constant protonation approach, which is something that if you already set up, if you run the command in GROMACS called pdb2gmx, you run into that problem. You had to take decisions. So you had to choose which protonation state should I use for this histidine or for that N-terminus. And you know the pKa's in water, and then you know that there will be a problem. You have to choose. And the moment you take a decision and you choose, then you are bound to it. And all the approximation that comes after are inherently tied up to your initial decision. And this is the constant protonation. And of course, almost all the world uses constant protonation, and that there's no harm done if you are aware of the approximation. Then you can take a better decision on how to choose the protonation state. You can you can do calculations a priori and try to estimate what would be the most probable protonation state in my whole protein, right? So this is something that you need. Of course, ideally, it would be so nice to just choose pH 7. You write down pH 7 and say, now my simulation goes ahead and it will sample all protonation states, all combinations that will be typical of pH 7, that will be usually available in the Erlenmeyer full of my protein and water and salt. And at least you know that those protonation states will be sampled, and you want to do that in your simulation. And this is what we have and what we use here. Of course, but let's go back to constant protonation. The moment you choose and you are one to do molecular dynamic simulations, you identify right away which are the charge / ionizable residues. Of course, we can claim that arginine is charged and it's very, very rarely ionizable because it has such a high pKa in water. And but all the other residues, you have to take decisions. And sometimes if it's a carboxylic acid, if it's like a glutamate, you might say, okay, glutamate, aspartate, pKa's of 4 and 4.3, maybe they should be ionized, and everybody will ionize them, unless you are in a specific position where ionization, when ionization will not be this ionization of these residues will not be the most important protonation state. And once you start the simulation, I want you to imagine that a certain residue that at the beginning might make sense to be neutral, after a small conformational rearrangement, the most preferred protonation state might be ionized. And then you took the decision. If you took the decision of keeping it neutral, you might be impairing and not allowing the protein to actually sample those conformations conveniently because of the decision you took right in the beginning. Yes, of course. If you start with the protein structure, there's more scenarios, of course, but I like to print out these two. This is the most common one. You might pick up an X-ray structure from the PDB databank or from some experimental colleague, or you might already start from one conformation of the protein that came out from a computational project, or from some solving from NMR, for which the NMR group actually ended up minimizing the energy of the structure before providing and giving it to you. So if this is true, then you have two different scenarios. And I want to bring up these two scenarios because this is the most common thing that you'll find out, even in this workshop. The decision will be, okay, I need to know the pKa of each and every titerable residue in the protein, because if it gives me a pKa of 2, I know that it will be deprotonated. It doesn't matter if it's a cationic or anionic, the charge will change, but you know that it will be deprotonated, but because the pKa is 2 below 7, and you want to run a simulation at pH 7. If the pKa is 10, then you are kind of safe to use this residue protonated. But now comes the problem. There are residues that will have a pKa very close to 7, as I mentioned. And another thing, the structure from which you start by doing the pKa calculations, the structure might be an average structure, like in the X-ray. And from that, if you do pKa calculations, if you try to estimate the pKa of those groups, you might have a good estimation. But quite often, if you start from a computational structure, that structure is already biased. Because if it was used in the computational project, or if it was minimized or whatever, if you apply the force field on that PDB file, the person who applied that protocol already took the decision from you, because you already set up the protonation states of the computational protocol. And hence, if you say that the glutamate is deprotonated, even though it might not like to be deprotonated, all conformations, all energy minimization protocol, all MD conformations will come biased towards the decision at the beginning. And hence, that structure will no longer be good for you to estimate the protonation. And then even if you want to do pKa calculations, you end up having a very skewed pKa value and a very poor estimation. And how do you do the pKa calculations? Of course, you know some of these. Some of you know all of the servers that I'm going to show you. This is very known. H++ is a PV solver server. Delphi pKa from Alexov is also based on Delphi, so it's another PV solver. You have ProPKA, which is empirical one, heuristic, and this one is also very, very famous. A lot of people use it. And now, of course, you have our own PyPKA, which is the fastest, the best. Of course, we develop it, I have to say that. But believe me, this is really a very cool PKA server. And you can download the software, run it offline, you can run it online. And this will give you kind of all the settings that you need to change to run a very good estimation. Well, it doesn't do a miracle, because if your initial structure is not good enough, then you will have like strange pKa values, of course. This is the address, it's quite easy, pypka.org. And this is the paper. And I'm going to show you just what you need to do for you to have an idea of how simple it is to calculate pKa values. So you can just write down the PDB code right on that field that is highlighted, or you can choose an input structure and you can submit a GROMACS nomenclature file, or I think it supports also other force fields, at least the nomenclature. Internally, it will do the calculation using GROMACS parameters. And it also writes down a PDB file with the protonation states predefined for a given pH. So if you want at pH 7, you submit the calculation and it will change the name of the residues according to the final protonation and pKa. Here are some of the parameters. Most of the time, just to use the default parameters is enough. It's rather good, but you can change the range to speed up the calculation. You can change the protein dielectric and of course, salt concentration. These are like the bare minimum that you should set it up. Of course, if you use 15, if you use 0.1 is pretty common, and it will be almost instantaneously, because since we already calculated all the PDB structures from the PDB databank, if you choose default parameters and you write down your PDB code in it, it will be instantaneous because it will be a search in the database. All the pKa values will be printed in the output, just like what you're seeing now. So you have a full titration curve, you have kind of a summary of the settings used, and then you have the residue, you have the residue name, the residue number, and the pKa, which is actually what we want. Now comes the problem that I raised before. What if, even if you have an X-ray structure, there is no guarantee that the structure is kind of average structure and it's representative of both protonation states. Imagine you are interested in the given histidine in the protein, or a tyrosine, or another type of residue, and for you to have a good estimation of the pKa value of that group, you need that the structure be representative of either the ensemble of protonated and deprotonated residue. And this is very uncommon to have it. Of course, it's more common in the X-ray structure where you have several copies of the protein in the crystal, and when it's resolved against the electron density, it kind of does an average out. And things usually go wrong when you have a structure that is determined at pH 4 and you are trying to estimate the pKa or the protonation state at pH 7, because the structure at pH 4, some residues might be slightly skewed, so that might happen. But how can we solve that? The lack of representativity. Usually we introduce flexibility. We want to do something, a computational protocol that actually introduces flexibility and allowed for the side chain of those amino acids that are titrating to change, to relax, so that afterwards we can have a better assessment of their protonation profile. The problem is that the moment you apply a computational protocol, you start from an X-ray structure. You can start from an X-ray structure and you end up with a computational structure. So you applied conformation, but because you decided you had to take a decision on the protonation, you already like skewed the conformations, biased the conformations. And because of that, we usually don't do that. So when do we need to do that? It's when a given residue is so important. Imagine that you have a residue that is in active site, and the protonation state of this residue might be incredibly important for binding, for reactivity, for, well, you name it. So if you have this residue, there are methods that don't require advanced methods like constant pH molecular dynamics, but can actually target and try to estimate the correct pKa. And one of such methods is a simple linear response approximation. This was developed probably by Warshall. Well, Warshall will say that it was him, but I don't know if he was the first to apply this. Linear response approximation assumes that if you start from a topology where this, for instance, this is a tyrosine. The tyrosine on the left side is deprotonated, and on the right side is protonated. So if you start from a topology with the tyrosine deprotonated, and you run MD simulations, after equilibration, you can equilibrate your structural properties, and after that, you have conformations that are typical from the ensemble of the deprotonated tyrosine. So the tyrosine will start interacting with the neighbors and with the solvent in a way that is typical for the deprotonated tyrosine. Of course, the opposite will happen with the protonated. It will interact, and now it's when it's neutral, the tyrosine will be a hydrogen donor, will start looking for acceptors, and the ensemble of conformations will be different. After you have these two, you can go and select a number of conformations from one ensemble and from the other, use a pKa estimation software like PyPKa who does the calculations, and you have a bunch of skewed and altered, biased pKa values. And this is like a kind of difficult to interpret, or can be difficult to interpret, but concentrate on the Y scale. On the Y scale, you have the pKa. So on the blue line, you have the protonated ensemble. So you have several conformations that will be averaged out in each of these points. And then we are trying to estimate what is the pKa at each pH. And the reason why we do this pH versus pKa is because for this approach, the pKa value of the group depends on the pH. That happens because this is not the only group that is titrating. There are many other groups around in the neighborhood that are also titrating, and they will influence the pKa. Otherwise, we'll be just averaging out. But this is what we usually do. So we have something like this, and we can plot the pKa values for the protonated ensemble. You see, it can vary from like 10.5 or 10.7 to almost 14. So you have list a group of pKa's. You could average something out. It will give you something like 12.5. So you will be somewhere around here, right? But then you go into the deprotonated and you will start getting something around 7, and a range from 6 to 10, and you'll get something around 7 or 8, somewhere around here. So if you have these two values, none of them is a good estimation of the pKa, because both of them who are skewed are biased. So if you kind of averaging out, here we are not averaging the pKa's, we are averaging the pKa is dependent on pH. And then we have this olive colored curve. And when this point here is when the pH equals pK. And this is where we extract the pKa. So this is the kind of average pKa, and it's like the best estimation of a pKa value that you can get. We can, of course, we can think about it and say, okay, but I can do that for one residue, but I cannot do that for 30 residues for which I have to take a decision, because that will be nightmarish, right? You end up spend a lot of time trying just to estimate the initial pKa's. And to take a simple decision, of course. So this methodology is limited in that sense. It's useful when you are interested in one specific residue or in a short number of residues. So when you have a full protein with a lot of important pKa values that you want to make sure that they are correct, then you need one of the many constant pH molecular dynamics approaches that are available to you. And this kind of approach is usually a way, it requires a way to couple protonation or proton binding affinity method that is able to calculate this pKa or proton binding affinity, and coupling it inside the engine of the MD. So you should be able to use like GROMACS to sample the conformations, and then use an external way to estimate the proton binding affinity of a given group. So if you know that this group now likes to be protonated, you protonated it, and then you continue the simulation. And if you afterwards the affinity changes, and then it does not like to be protonated and prefers to be deprotonated, and then you deprotonated it, and then you continue. So if this is done correctly, there are many methods that some use Rice-Born, others use Poisson-Boltzmann, and there's lambda dynamics, all sorts of ways to estimate how much does a given group likes to have a proton. So in this method, this is like one of the first methods developed for constant pH. It's the stochastic titration method by Antonio Batista. And in this method is quite simple. So you run MD, you stop, you pick up the conformation that the GRO file, so the conformation that was just written, you go into Poisson-Boltzmann, you calculate pKa values, and you calculate populations that comes from the pKa values, and then you get from that, you get the energies, and then you go into Monte Carlo, and then you inject these energies and allow the Monte Carlo to calculate which are the preferred protonation states. And once you get that protonation, a new protonation change state, you go back into the MD, you change the topology. Now it's like too technical, you can do it several different ways. You change the topology, and then you continue running your GROMACS simulation. So if you, with this, there's a small caveat, which is the moment you change a protonation state, there is a small step of relaxing the solvent, because the pKa calculation was made assuming that the solvent would be relaxed for either states. In MD, if a protonation state change occurs, the solvent will be relaxed and will be appropriate only for the initial protonation. If you change to another one, the solvent will create kind of a clash, and then you have to relax it. But this is like cyclic. You do it in small increments. The MD trajectory is kind of growing, small steps by small steps. And there are a few files that are written with the protonation states. In the end, if you run the simulations at different pH values, you can actually get titration curves. And now our code is old, and it's like we never, every time we shared our code, there was always a big learning curve for everybody new to learn it. So now we have a new version for it. So it's like a Python powered version of the constant pH, and it's available on GitHub. And it's still, how do you say it? It's still being tweaked with, but now we end up having this interface which is very clean, as you can see. We can make it run with just very simple group of settings. There are a lot of parameters that are just hidden and they are just not important. But if you define a few variables like names of files and for input and for output, of course, if you have to define which sites you want to titrate, the number of cycles. So this will end up also being grouped together with the frequency at which we calculate the pKa values. And of course, it works for GROMACS from 5.1.5 to the most recent ones. The reason why we still have a version that is compatible with 5.1.5 is because this is the last version that is still compatible with reaction field. So we often do constant pH molecular dynamic simulations with reaction field and with PME, and this is quite common. And the reaction field is very nice because then the charges that are changing it is not required for us to actually neutralize the box, the simulation box. So it's an advantage. It has other disadvantages, of course. We have to bear that in mind. And at the moment, we are like final debug. I think we are kind of confident that everything is running smoothly because we are comparing with the previous version to get it really giving the exact same results for all systems. We are just now validating and doing these final tests. And what is missing is actually a tutorial that will be probably, if this meeting would be in 1 year from now, we will have a tutorial to teach you how to use PyPKMD and how to do constant pH molecular dynamics. Now I have a little bit of time, so I'm going to give you a few examples. of how can we apply this constant pH molecular dynamics. Some of these applications are rather simple, like if you pick up a protein and you run constant pH molecular dynamics at different pH values, in the end, you do titration curves and you have a table of pKa values. You can compare with experimental. You can see if you have a good RMSE, if you can, if your method can capture correctly the macroscopic pKa values. And this was what we were doing like 10 years ago, and it was very fun. But now it's not fun anymore. Now we want to do like, we have a big monster of a method, and we want to apply it into very interesting projects. Imagine, this is a very interesting project. So imagine if your drug is entering a pocket. So this is donepezil, which is like an Alzheimer drug that is given. It inhibits acetylcholinesterase, is like this big chunk of a protein. And the thing is, there is an histidine on the pocket, whose protonation state can change. And the drug itself, it's a tertiary amine, so it has a pKa of around 8.5. So it has this high pKa value, which the moment the drug goes into the pocket, the protonation in water, which is like +1, you can see it here, the moment it starts decreasing the distance to the pocket, this is the X-ray pocket, so the moment it's reached, you see that now the protonated form is no longer the most stable, and then it passes a region. So in this region around here, it's when the drug is going into the pocket, and if there is a group that accepts the proton of this drug, this compound will gladly give the proton away, at least transiently, right? And then it will enter the binding site, and the moment that it binds into the the final position, and it reaches the X-ray position, which is like this is in blue, then it's funny that the drug or the ligand actually has an average protonation of 0.5. So this would be a nightmare for MD, right? If you want to study, use MD we would have to do both protonation states of the ligand, and in the end try to do some sort of averaging out, because otherwise, if we choose one of them, we are only seeing half of the ensemble. We are not seeing it all. Now, this is also another interesting. This is just like to illustrate the applications, right? So this is oleic acid. So it's like a big tail of hydrocarbon. And then there's the carboxylic acid on top. And this carboxylic acid, it has a pKa of like 5 or so, or 4.7 or 5, I can't remember. And this pKa value in water has nothing to do with the pKa and the preferred protonation state when the oleic acid is in water and creates something like oil droplets or micelles or, and of course, lipid bilayers. It forms lipid bilayers at certain conditions. Now, if you change pH, you see the whole lipid bilayer that we can construct. If you change pH, if you start increasing pH, you increase the amount of groups that will get ionized, and then the charge repulsion is so high that you just like explode, and then your lipid bilayer transforms into micelles. And this is what we know, that after pH 8 or so, or pH 8.5, we know that somewhere around here, the system kind of explodes experimentally. So this would be a very nice, or this was a very nice system to test, because we wanted to see if the constant pH molecular dynamic simulations work nicely in membrane environments. Other things that we can apply is, what if we have like peptides or drugs interacting with the bilayer? Because the pH is a property of water. pH is a bulk water property. The moment you start going into this like water membrane environments, interfaces, then pH kind of changes, and it requires the availability of protons. Protons are now not always available. They will be available until a certain depth into the membrane, after which you have an energy. The pKa is no longer a macroscopic pKa. It's like a proton binding affinity. It's like an energy. Your method can estimate that value, but if you don't have water nearby, it doesn't matter if your compound wants to get a proton if there are no protons available to to sequester. So this is also another kind of system that we have, and here is one probably of the most complex one. It's when you start having like peptides and proteins embedded in the membrane, because then if you have something on the outside, it's like solvated in water. If you have something on the middle, there is no water, so there's no pH. If you have something at the interface, then you can start seeing things shifting and start capturing the dissolution effects. So how does the fact that we start having less water available affects the proton binding affinities, how much a group likes to be ionized or neutral. And this is also, I'm going to give you some example of this. And for that, I need to just to show you one or two slides to bring you into context. So one of the main causes of drug resistance nowadays is has been related with the tumor acidity. So this tumor microenvironment, whenever we have a tumor, we start having some sort of acidity, and this is the difference in pH is very small. It's like the experimentalists have a hard time trying to quantify these small changes. We are talking about coming from changes of 0.8 to 1 pH unit. But we all know that as this acidity, every time we have a tumor, and we can see with all these probes, we can see the tumor mapping, we can see the acidity accumulating. And we also know another thing is that the more aggressive is the tumor, the more acidic it is. So we know that the tumor generates acid, and this has been used to develop technologies like the flip peptides, and there are some compounds like these peptides that can do something completely different from what is happening in water once they encounter two things: the membrane and acidity. And for this case, they are unstructured in water. They will adsorb into any membrane that we add, and then if we acidify, the peptide will tend to fold into an alpha helix and insert into the membrane. So if you have a peptide that can do this at one specific pH, like 6, 6.5, but not at pH 7, 7.5, then you would have the perfect probe that will target specifically tumors. Then you could use this to mark with probes, mark tumors, just like they did with this poor mouse, where they just mark the tumor, they introduce the tumor, and then they use the flip with this probe to actually see the probe. Of course, there are some natural tissues in our body that are acidic, but as long as you don't have a tumor in those tissues, the technology works and holds. And this is the experimental titration curve. This is where the experimentalists, when we were like defining or designing the project, they were coming to us and say, okay, we know that the pK of insertion is 6. So we know that once you're coming from pH 7, the moment you start reaching near pH 6, we start seeing like folding and insertion into the membrane. And this was nice. Then we defined the way to model this with the computer, and we just introduced the alpha helix into the membrane. We know there are some titrable residues. We concentrate in all of them, try to find out how does this helix holds in the membrane, and then the moment we run this constant pH molecular dynamic simulation at different pH values, we were allowed to slice the system along the membrane insertion pathway. It's kind of like when you're going inside the membrane. And by having all these conformations and protonation states kind of sliced in different, let's call it umbrellas. If you have those, then we can separate the ensemble along the membrane normal, and we can calculate pKa. Of course, at some point, we stop being able to calculate pKa, because at some point we only have the group, the titrable group, which in this case is this aspartate. We start having only the neutral form. If you don't have charge form, you only have the neutral, you cannot estimate the pKa. You need to average out between protonated and deprotonated to calculate pKa's. And this is what we did. This is just to show you some data. And we calculated several methodologies. We use pH replica exchange. We use constant pH. Of course, pH replica exchange helps a lot. We use different sizes because the peptide is very large. We didn't know how many lipids we require. And we just found out that, okay, as long as you don't choose 128, which is very small membrane patch, all the others kind of converge. And this tells us that once we are at the region where water starts to become scarce and almost unavailable, which is like around -6 in our insertion measure, then our pKa came from the water pKa, which is right here. It just shifts due to dissolvation and the interaction with other groups, and then it ends up going into like 6.05 to 6.45. So we have like a big chunk of data around here. Of course, we don't know how large is the pKa of the experimental, but we were very happy that we could reproduce exactly the pKa. Now the question is, can we change the sequence? Can we make the peptide faster in terms of kinetics? Will we have problems with the pKa of insertion? Does it change? So this is what we've been doing in these last few years and try to assess and try to evaluate how much we can change without kind of ruining the technology. And it's always cheaper to do it in the computer than to actually go and start killing some mice. Okay, so now that you grasp the idea of this tumor-induced acidity, this slide is just for you to introduce another concept. So in a normal cell, the pH is around 7.4 on the outside, and the tumor cell, which is the tumor microenvironment, let's call it like somewhere between 6 and 6.8. Of course, 6.0 will be the most aggressive tumor. Inside, it's not many change. It doesn't change much. 7.2. Some authors claim that inside tumor cells, the pH is slightly increased, somewhere around 0.4, 0.6, 7.4, 7.6. And now this is the new thing. Lysosomes. We know lysosomes are like the trash bin of the cell. So every time you have something that the cell wants to get rid of, it just kind of directs it into the lysosome, but also peroxisomes and other organelles. But lysosomes are known for this. And lysosome has this characteristic, which is it has a pH very acidic, somewhere between 4.5 and 5. So if you have lysosomes that are incredibly acidic, what happens is some of the compounds that are used to treat tumors, so these are anti-tumor compounds, chemotherapeutics, if you like it, like sunitinib, daunorubicin, nintedanib, and vincristine. Some of these compounds, they are usually in water. They are usually Lewis bases. They are charged positively, and if you have this positive charge on them, it means that they have trouble to cross membranes. So their membrane permeability, the ability to cross membranes and enter cells, is kind of limited. So how does that work? Usually it works because the pKa, they are Lewis bases. It means that the pKa is not very high, and it's like a weak base. And these weak bases, they have pKa's that once the compound reaches the membrane, they can transiently deprotonate. I'm going to bring you these 4 examples and show you the pKa values. Otherwise, you have no idea of how much does it need to change the pKa to actually cross the membrane. So it's not much. You see, the highest value will be 8.5. So if you have 7.2 in a normal cell, so it's not that much. Once these compounds enter the membrane, this pKa probably will shift enough for the molecule to transiently deprotonate and cross the membrane. And sunitinib, you can see it's a tertiary amine. It's the proton is located there. The neutral form is when you lose this proton, and in water it doesn't change, the conformation of the molecule doesn't change much. And if you run simulations in water, you'll realize that at pH 7.2, around here, most of the compound will be protonated. I would say that 95% of the compound is protonated, probably only like 5 or 6% of the compound is deprotonated. So how does the compound permeates and crosses the membrane? So it just changes this proportion. And how do you change this proportion? Is you interact with the membrane. The moment you interact with the membrane, the proton binding affinity changes, and now the compound prefers to be neutral. And then this way it will allow to transiently deprotonate, give away the proton on one side and appear on the other side, and then capture a proton somewhere from the solvent so that it can release the membrane and go away. So the problem about doing a model to learn how this process happens is that when we run MD simulations, the insertion level that we can sample is somewhere around -5 and +5, because these compounds are hydrophobic. So they tend to go into the membrane interface right away. Once they are at the membrane interface, they are still too polar. There is a barrier for them to actually cross to the other side. And unless we force them, they just don't go. They just stay at the interface, quite deep inside, but they have a barrier at the center of the membrane. This way, if we run simulations, we'll have sampling from here going to the interface, and then at some point we'll lose sampling, just like the project that I showed you before. And this can be kind of illustrated by these curves, where you can see this is like an histogram of abundance dependent on the membrane insertion. And this is the protonation. So if the compound is on the water phase, it's mostly protonated. It's mostly protonated. This is +1 protonation. This is neutral. And you see the moment the compound starts interacting with the membrane, it will lose the proton. So, and goes into 0 protonation, so 0 charge. This is true. And this is particularly remarkable and easy to happen at pH 8.5. But if you decrease pH, and now the pH is 7.5, you see the same profile, but it's shifted. It's shifted because at pH 7.5, the pH will favor more the population of protonated. And of course, this will happen at 6.5, and you are increasing acidity now. And at some point, like at 5.5, it will be very difficult for the compound to deprotonate, and we lose sampling right away. So at this point, we don't. Of course, the compound will go inside, but it will stay neutral, and the sampling will be very difficult. And when you look at the abundance, we see that at acidic pH, it prefers to stay at the interface. At more basic pH, it will internalize into the neutral form. And with this data, we can do this. We can calculate the pKa along the membrane insertion, and then you have something like this, where this is the pKa in water, so it's the 8.5 that you saw for sunitinib. And the moment you start going to the membrane, it feels like choline, it feels phosphates. So if you see this kind of a dance in the pKa, and then it goes into deeper locations, and the pKa gets shifted like to 5. This is all interesting, and you can see that for vincristine, the profile is the same. Nintedanib it's more hydrophobic, so your profile is slightly shifted, and you have all of that. But I want to call your attention to what happens if the cell is a tumor. It means that if you concentrate in this region of the pH, it means that some compounds will be able to cross and enter the tumor cell, which is desirable, by the way. They will be able to do that, but other compounds will require like a higher energy. So they will require a larger push, just like sunitinib and especially vincristine. The fact that they only get 50-50 in population, because this is the pKa, they only get this at this deep in the insertion, it means that they just don't want to cross the membrane. And this is the pH range for lysosomes. What this means is that compounds like sunitinib and vincristine in the tumor, if they get inside the cell, and also in normal cells. When they get inside the cell, right away they go into lysosome, and in lysosome, because the pH is so low, they will get trapped there. So they will get inside, they get protonated inside the lysosome, and now they cannot come back. It's called lysosomal entrapment. It's something that is known for quite some years, and this is like a major problem into drug resistance chemotherapeutics for tumors, drug resistance in tumors. So this for all chemotherapeutics that are how do you call it, Lewis based. So not all of them are, of course. And this is just a slide that shows you that this is not only exclusive from chemotherapeutics. There are other drugs, some of them like antipsychotic and other like central nervous system drugs that they require to cross the blood-brain barrier. And for so, they kind of were selected in the drug selection protocols by experimentalists, by pharmaceutical companies. They were kind of selected because they have the perfect solubility. So they are soluble in water, they transiently deprotonate, and then they become soluble again on the other side. So this is perfect drug, right? No, because all these compounds actually get easily trapped into the lysosome. Once they reach, they need to evade all lysosomes. Of course, in tumors it's worse because one of the processes that tumors can create to create another level of resistance is tumors can generate more lysosomes. They activate the number of lysosomes. They can have up to 6 times more lysosomes. So imagine, a compound goes into a normal cell, and if it evades lysosomes, it can act on a normal cell, can actually kill the normal cell. If a compound interacts with the tumor cell, it requires to actually do its job, it requires to evade 6 times more lysosomes, which is a real problem. And this is probably one of the last slides that I'm showing you. This is just for you to have an idea that we can calculate membrane permeabilities. And for the case of sunitinib, remember this is like pH of we choose these pH values that are typical of the lysosomes, typical of a tumor cell, a normal cell, and the control at high pH. And we did the simulations and calculate permeabilities this way. We can calculate PMF using umbrella sampling coupled with constant pH molecular dynamics. And this way you can have like an energy profile of the sunitinib compound crossing the membrane from water to the membrane center. So the 0 corresponds to membrane center. So 40 will be like water. And with this, if we have enough sampling, we can calculate permeabilities. This is a nice chart. This is the last data that I show you. But I want to call your attention for the difference between pH 7, let's see, normal cell, tumor cell, right? Lysosome, I already convinced you that lysosomes, they all get trapped. So it's like a big black hole in the cell. But if you use Lewis drugs, what this graphic tells you for the case of sunitinib is that you have a huge membrane permeability. You have a huge facilitation for this drug to actually reach the inside of a normal cell. And you have so much lower permeability for a tumor cell. What this tells you is that in this graphic lays probably the reason why most chemotherapies actually generate so much side effects. Because it seems like when we use these Lewis drugs, we are increasing so much the ability of this drug to enter a normal cell compared with the tumor. The tumor finds ways to evade, and the drug becomes problematic. And this is what happened with these compounds. You see, you have protonated neutral on this side. They can cross to the other side, no problem. And some of them get trapped, others stay outside, and these guys will create toxicity. As you can imagine, this is a normal cell. And so all these guys that stay here will create toxicity. On the tumor microenvironment, you see that most compounds, many copies will stay outside because they need to neutralize to cross to the other side. And the ones that actually cross will accumulate in the number of lysosomes that are available. So only these guys here can actually go and do the treatment. So this is kind of very, very ingenious and simple anti-tumor drug resistance mechanism. So this is just a simple question for you is, do we actually need them, these Lewis base? Of course, they give incredibly good solubility and they require, otherwise, most of these hydrophobic compounds will never be soluble, will be very difficult to do a treatment. And some of these compounds, some of them are actually pills. It will be impossible for you to take it as a pill if it would not be a Lewis base. On the other hand, just based on electrostatic reasoning alone, if we change the amino group, which is a cationic group, by an anionic group, if you just change this, the whole membrane permeability paradox of having higher permeability in tumor drugs will be reverted. So technically, what we want instead of a weak base is a weak acid in some of these compounds. If we are able to change weak base, Lewis base, by a weak acid and still get enough binding into their target, like here you have tyrosine kinase protein. So if you are still able to find a good drug that binds there and carries a Lewis acid, then you might have an incredibly more powerful anti-tumor drug with much less side effects. But this is just food for thought, and it's something for you to carry home. And it's a point that we are actually following. And this is just to thank, I think my time is up. Just to thank all the guys, my PhD student. Pedro is the one developing all the PyPKA derivatives. With Tomas did most of the work with the flip peptide, and well, all the master students are actually working in this or something related to what I've shown. So I thank to all of them and the funding. And thank you all for watching.
So thank you, Miguel. We have a few questions for you. It's on a live document that you don't have access. So I'm going to read to you if you can answer.
Cool.
In which way can we handle the protonation and the PK changes in protein ligand binding in MD is the first one.
In what way?
In which way you can handle the protonation and the PK changes in protein ligand binding in molecular dynamics? Yeah,
we need an unsampling. My experience is that the moment you add the ligand and let the ligand just relax to the pocket, and we start having a lot of sampling issues. We actually need to have a very good sampling of the interaction between the ligand and protein. And we all know that it is tricky, it's not simple. And not all ligands are very good binders. They tend not to stay too long in the same place. So we need something that enhances sampling. What we've been using and what I used in the example I give in the presentation was umbrella sampling, simple umbrella sampling, and coupling with constant pH. Instead of coupling umbrella sampling with MD, I coupled it with constant pH molecular dynamics. And then in each umbrella, we have a constant pH and we know the protonation. We need to do the real weight because we are introducing a bias. We need to remove that bias from the protonation. And once we do that, well, it's just like how you heard from Burkess before. You introduce a bias, you solve the sampling, and hopefully the protonation comes along with the confirmation coupled together. Yep.
Okay, so thank you. And the second question is, how does your software performance compare with the available ones, specifically on computational time and the overall performance?
Mm-hmm. Yeah, that's a good one because there is no clear answer, because it will depend on the size of the system, and it will depend on, because our methods still, this method that I showed you still requires Poisson-Boltzmann calculations. That is something that we plan to change, because now we have an AI based method that can actually perform very similar to Poisson-Boltzmann, and that will be almost costless, which means that we'll be able to run MD simulations, constant pH molecular dynamics, almost at the same computational cost as MD. But that is still in the works. It is Pedro is working on it, and at the moment we have something. As a rule of thumb, we say that to run our constant pH molecular dynamics, it takes twice as much time as to run normal MD, because an average number of sites that are titrating, that average number of sites usually takes almost the same time as MD. This, of course, if you only have one site in a large protein, this will be a very bad estimation, of course.
Okay, so thank you so much, and thank you for your presentation.
So I actually had one comment and one question.
Okay.
So the comment is that the constant pH in D is something that is a part of the BioXL COE. So there's work going on in Stockholm under Burkess and in Jyväskylä under Herrenhoff on this, but it's still in fairly early stages.
I've been following, yes.
Yeah, so there could be some potential for overlap there. But so my question is, what I'm curious about is, to what extent is your method just hacking the topology file versus having to hack like the core of GROMACS?
Oh, good question. Like, how difficult would it be technically to actually create an add-on to GROMACS?
Exactly, yeah.
I think that we are at a level now. We are at the level of what we are doing with the topology that would be incredibly simple, I would say, because we don't have any plans to do that because there's an elephant in the room, and that is the elephant that I know that probably Garrett is working also. It has to do with how do you balance the charges, because if you were, in my case, because I'm too focused on Gromos force fields, I can take the advantage of using, for many projects, I use reaction field and generalized reaction field. Even though, for instance, for membrane systems, it's inadequate to do so. But the moment we go into PME, then we start having this problem. PME has some requirements, and the way to deal with electrostatics of a system that whose charge is changing over the simulation, it's not obvious. It's the main problem with the method for Brooks, both methods from the Brooks brothers. It's the problem that the lambda dynamics methods have. I think Garrett's method is based on lambda dynamics. Everybody will have this problem. We know that we have this problem in some projects. As long as the moment we know that this is inadequate, in some membrane protein projects, we need to go to PME. Otherwise, we know that the approximation is too large. It's inadequate to use Gromos with reaction field for that. And once we have in this project, we start having the same problems as everybody else. And this is the rate limiting step for constant pH molecular dynamics. Last time I spoke with Bernard Brooks, what he told me is that now he has the perfect PME. He has a Evel summation method that will actually solve all the problems of charge fluctuations. I'm still waiting for that. Once that is available, and well, or someone else develops that for GROMACS, I think that it would be so nice for GROMACS to have at least two constant pH MD methods. One that is continuous, the one that you are working in Sweden, and the one that is discrete, which is the one developed here in Portugal. I would say that if we manage to introduce this into GROMACS, it will be incredible, because they are for different problems, they are so much better than the other one, you see, when simulating in terms of convergence. And thanks for the question.
I can just comment that his charge problem we have solved. So I think other people have similar. There are similar solutions also around, but we have buffers in the solvent that get charged up, so the total charge of the system remains constant. So that problem,
like
that problem is solved.
did that also. In her case, I don't know. I didn't test it yet, but for the case of Yannishan, she has real problems of conversions because of that.
No, we don't see any problems there. So I mean, we have that working.
Well, maybe it's solved. Yeah, that would be perfect.
Yeah, we think so.
Yeah.
I mean, it should work, right? This is also how some alchemical simulations work.
Yeah, but you need to compensate for the cost of creating the charge in the sol, or not creating charge for changing the properties of the buffer molecule. But that we're doing. So yeah.
It's. I think it will be nice, and in our method it doesn't change much because the fact that it requires some external calculation of the energies, because it's using an external calculation of the energy. This external calculation will be, as I said, it will be costless in the future. That is something that we are really hoping for. Nice. So I stop sharing.